Hi guys, in this unit we will be covering fault analysis. That is, we will be analyzing the power system under faulty condition. Now faulty condition may be due to a lightning stroke which may strike a transmission line. There may be insulation failure. If insulation fails, then the line will be connected to ground via the tower. That will cause current to flow into the ground. That is also a faulty condition because no current must flow into the ground from the transmission line. Or due to short circuiting. These sort of conditions will lead to the faulty operation of a power system. Now why do I want to analyze these conditions is because somehow if faulty conditions comes in a power system, then I must have analyzed it beforehand so that when the condition comes, my system must be prepared to tackle the fault. That is, the protection system should be present in a power system which should be able to deal with such faulty conditions. That is why we want to analyze the faulty conditions in a power system. Okay. So fault analysis is done only for design of protection system. Now for the purpose of fault analysis, first we must have an understanding of how we represent the power system in terms of its equivalent circuit, so that whenever there is a faulty condition I can analyze that network and determine what will be the voltages and currents under faulty conditions. So power systems is usually represented using a single line diagram. Single line diagram means all the components that are present in a power system are represented in a single line or are represented in a linear manner. Now what is the advantage is it is more readable. How it is? Because if we were to replace each component by its equivalent circuit, then it will become very tacky. Now if you see here, there is only one transmission line. Okay, but in a practical power system there will be hundreds of transmission line, so hundreds of transformers and hundreds of generator. So it will be very difficult to represent each component with its equivalent circuit because then the end user may not be able to read the whole schematic. But if you represent in this manner, here G represents a generator, this is my transformer. So one transformer will be step up because we need high voltage for transmission. Other will be step down because load will be supplied at a lower voltage, and in between there will be a transmission line. So in this manner I can easily understand the topology of the power system. It is called as a single line diagram. Now let us look at the equivalent circuit of each and every component that is commonly occurring in our power system, so as to understand how does the equivalent circuit of my power system looks like. So the first component is my generator. In synchronous generator, how we represent it? We represent it using a EMF source EF angle delta, then armature resistance and synchronous reactance. So here by default I am assuming that it is a cylindrical rotor synchronous generator. Later I will tell you the reason why I am neglecting the salient pole and only using the cylindrical. Okay. So this can also be represented if RA is neglected, something like this. The reason for neglecting RA is that whenever the fault will occur, then what will happen? High current will be encountered, and that high current will be reduced due to the presence of armature resistance. But we always want to do the worst case analysis, that is, we want to analyze the highest fault current. So we will have to take the impedances as minimum, or we have to neglect everything that will make the system stable. That is why we are neglecting the armature resistance. So this will be the equivalent circuit of the synchronous generator. Similarly, for the case of motor, The circuit can be represented as this will be J-axis, EF angle minus delta, and this will be VT angle 0. So this will be the equivalent circuit of generator and the motor. Okay, usually we neglect the resistances in both type of synchronous machine. The next component that we connect in the power system is either a step up or a step down transformer. Now transformer has a turns ratio V2 by V1 will be equal to N2 by N1, we call it as K. Now usually if we neglect the shunt parameters, why I am neglecting shunt parameters? Because no load current in a transformer is much less as compared to full load current or the fault current. Fault current is even 10 to 20 times the full load current. So no load current is negligible as compared to that. Hence we can neglect the shunt branch parameters or the no load current. So then we will have only the series impedances on primary as well as secondary. Now we know in a transformer we can refer the impedance onto one side. So if we refer the impedance onto primary, then it is called as Z01. The circuit will be something like this. Z01 will be equal to Z1 plus Z2 into N1 by N2 whole square. That is Z1 plus Z2 by K square. Similarly, we can form the circuit referred to the secondary. At the secondary side, this will be Z02. Now, what is the value of Z02? Z02 is Z2 plus Z1 into N2 by N1 whole square. This we have covered in electrical machines, that we have to multiply by the turns ratio square to transform the impedance, that is Z2 plus Z1 into K square. So that will be the equivalent circuit of our transformer. So remember, here we are neglecting the shunt branches because the impedance or the no load current is negligible as compared to your full load current and the fault current. So we have to neglect the no load parameters. In case of transmission line, we saw three models. One was short transmission line, in which we considered only the series impedance Z. Then one was a medium transmission line, in which we looked at four models, that was receiving end C model, sending end C model, T model and pi model. And the most famous is pi model, in which we represented like this: Z y by 2 y by 2. And the last one was long transmission line, where we use distributed model. Now here we will either consider this short transmission line approximation or the pi model, but not the distributed model, because though the distributed model is most accurate, but the problem is that analysis will be very complicated, as in a practical power system we will not have a single transmission line, but we will have hundreds of transmission line. So those equations will be complicated to analyze, and this model is the most common, which is a short transmission line. So in most cases you will see that the transmission line will be represented just as a series impedance. So remember this, transmission line is mostly modeled as a series impedance and nothing else. And at last, the load in the power system is represented as resistance in series with reactance. Why only reactance? Because most common occurring loads are lagging power factor loads, RL and XL, that is the load resistance and the load reactance. Okay, and this will be neglected during fault analysis. Now why do we neglect the load impedance? Because suppose a short circuiting comes in a power system. Now as we know that the current will try to take the path of minimum resistance or the minimum impedance. So it will try to go into the ground via the short circuit. So if it goes into the ground, then the current going into the load will be very low. Okay. So that is why we can neglect the load on the assumption that all the current flows into the fault and none of the current goes into the load. On this assumption, I can neglect the load when I am doing the fault analysis. Now let us combine these models and try to form the equivalent circuit for the single line diagram that we saw earlier. So generator will be modeled as a reactance in series with EMF, let us say EG. Then there will be primary impedance, let me say Z01. I have referred the entire circuit to primary. This is transformer secondary. This will be Z line. Okay. Then Z01 dash. This is the primary side impedance of T2 or the impedance referred to primary for T2. Then this will be the secondary winding, and here we will have the load. Now if you see here, if we want to analyze this circuit using the mesh analysis, we have to form 3 KVL loops, I1, I2 and I3. So if you see, this is all happening because this transformer has divided the circuit into or the network into multiple sections. And this is the case when we only have a single transmission line. So try to imagine what will be the case when we will have a practical power system network which will have hundreds of transmission line. Then the effort involved will be unimaginable. Okay. So there will be so many equations that you will not be able to solve those equations. That means we need a way out by which we can simplify the analysis of the power system. We need something or some method which can reduce the effort involved or which can reduce the number of loop equations that we have to form to simplify the network. That method is called as your per unit system. So per unit system we covered earlier. So I am just revising the basic concepts. Here I told you that we assume two base quantities. One is your voltage base, other is your power base. Then in three phase, current base was S base by root 3 V base, because this base voltage was line to line voltage. Then we saw Z base in star connection was V base square by S base, whereas Z base in delta was 3 V base square by S base. Okay. And we saw whenever we want to change the base from our old value to new value, we multiply it by old voltage base by new voltage base whole square, new power base divided by old power base. So these all expressions we saw in the first unit. Now we will be making use of these expressions when we will be simplifying the networks or representing the power system in terms of per unit. But let us first see what happens to the equivalent circuit of the transformer when we enter the per unit system. Okay. So here the first problem with transformer is that the transformer rating will be something like this, 33 kV by 11 kV. Then how to assume the base voltage, because here there are two rated voltage, one on the primary, other on the secondary. So what we will be doing is separate base for primary and secondary. But we know one thing for sure is that transformer cannot generate power, so power remains same on secondary and the primary side. So that means V1 I1 will remain same as V2 I2, which means I1 by I2 will be equal to V2 by V1, which will be equal to K. S1 should be equal to S2. So power base will be assumed as the same value on both primary and the secondary, but your voltage base will be different. That will be dependent on the turns ratio between the primary and the secondary side. Now, since voltage base is different and power base is same, that means the base impedance will also be different. So let me say V1 is the V base primary, I1 is the I base primary, V2 is the V base secondary, I2 is the I base secondary. Now if we want to calculate Z base primary, it will be V1 by I1, whereas Z base secondary will be V2 by I2. Now V2 is equal to KV1, whereas I2 is equal to I1 by K. So it is equal to K square V1 by I1 or K square Z base primary. Let me call it as Z1. So Z2 will be K square Z1. So that means base impedances are also related by the turns ratio square. Now we saw that the impedance on the primary, equivalent impedance was Z1, equivalent impedance was Z1 plus Z2 by K square. Now to convert it into PU, we will divide it by the base, and that base impedance will be taken at the primary. So Z1 plus Z2 by K square. Primary base impedance is, let us say, Z primary. So to avoid confusion, let me represent it by Z primary and Z2 by Z secondary. Okay. So this is your ZB. So this will be Z01 PU. The impedance referred to secondary was Z02 ohm was Z2 plus Z1 into K square. So Z02 in PU will be, this shall be divided by the base impedance on the secondary side because the impedance is referred to secondary. So that will be Z2 plus Z1 K square divided by ZB K square. So this will be Z2 by K square plus Z1 by ZP, which is equal to Z01 PU. So from here we can see, though Z01 ohm is not equal to Z02 ohm, but Z01 PU is equal to Z02 PU. So the per unit impedances referred to primary as well as secondary is same. But remember, this is Z01 and Z02. Still Z1 PU will not be equal to Z2 PU. Okay. So this is the impedances referred to primary and secondary. This is the primary impedance. This is the secondary impedance. This is the overall impedance referred to primary, overall impedance referred to secondary. So overall impedances are same on primary and secondary, but individual impedances are different on primary and the secondary winding. Okay. So when we are transforming the per unit impedance from primary to secondary, that will remain same. There is no concept of the turns ratio. Similarly, we assumed the voltage base at primary as V1 and voltage base at secondary as V2, which is equal to KV1. Now suppose some voltage is given at primary as V and the voltage at secondary will be KV. So in PU it will be V by V1. In PU it will be K by KV1. That is V by V1. So per unit voltage is same on primary and the secondary. Per unit impedance is same on primary and secondary. Per unit voltage is same. MVA is same. So per unit current will also be same. So each per unit quantity remains the same on primary and the secondary winding of the transformer. That does not change when we go from primary to secondary or from secondary to primary. So what happens is that if these quantities remain same, then the turns ratio does not matter anymore. So we can remove the turns ratio of the transformer. So if we remove the turns ratio, then what will happen? There will be only impedance of the transformer, that is, it will be represented just as an impedance, which is equal to Z01 pu, or you can say Z02 pu. There will be no turns ratio. So if we draw the previous circuit in per unit, there will be generator, reactance, then transformer will be represented as an impedance, then transmission line impedance, then second transformer, let us say Z01, Z01 dash, ZTL, then there will be load. So now if you see, there is only one loop equation needed for simplifying the circuit. Okay, this is RL XL. So if we represent the power system network in per unit, the analysis is very simplified because the number of mesh equation or the number of loop equations required are reduced. Okay, as the transformer turns vanishes, the number of equations will be reduced. Now let us see a problem how to analyze the power system in per unit, or how to draw the per unit equivalent circuit. So here we have been asked to draw the reactance diagram of the system whose single line diagram is given. Various ratings of the machines are given: generator 1, generator 2, generator 3, T1, T2 and transmission line. Now the first step that you must do is divide the power system into different sections based on transformer. So the circuit is shown here. Divide the power system into different sections. How? Like this. This will be section 1, this will be section 2, this will be section number 3. So I have divided the power system into 3 sections based on transformer winding. Now we must choose a base in any of these sections. So how to choose a base? If the base is given, it is fine. Otherwise, you have to choose a base for yourself. So let me choose the base as 30 MVA and 11 kV. That too in the section of generator G1. Now G1 lies in which section? G1 lies in first section. So here base is 30 MVA 11 kV. Now as we know that the transformer does not change the power base, the power on both sides of the transformers remain same. So base MVA in section 2 will be 30 MVA and in section 3 also it will be 30 MVA. But transformer does change the voltage, so we have to transform the voltage to find the voltage in section 2 and section 3. So remember, only one section out of the 3 sections is independent. You have to assume a value for that, and then the rest of the values should be calculated based on the turns ratio of the transformer. Now first transformer is 11 by 33 kilovolt. So since the primary voltage is 11, secondary will be 33 by 11 into 11, 33 kV. Now secondary voltage of T1 becomes the primary voltage of T2. So the T2 secondary voltage is, rating of T2 is 33 by 11. So T2 secondary voltage will be 11 by 33 into primary. Primary voltage is 33. So it will be 11 kV. So now I have got the base for all the 3 sections: 30 MVA 11 kV, 30 MVA 33 kV, 30 MVA 11 kV. Now the next step is to calculate the per unit impedances on the bases in different section. So let me start with generator G1. G1 impedance is given to be 1.6 ohm and G1 is lying in the section 1 where the base is 30 MVA 11 kV. So 1.6 divided by base impedance. Now base impedance is V base square by S base. V base square is 11 square by 30. Z base is V base square by S base. So it will come out to be 0.3967 pu. Okay, so whatever the base you are choosing, that will depend on in which section is the device lying. Next, for generator 2, it is 1.2 ohm. Generator 2 is lying in which section? It is lying in section number 3. So 1.2 divided by, in section 3 base is 11 kV 30 MVA. 11 square by 30. So it will be how much? 0.2975 pu. Similarly, generator 3, it also lies in the section number 3. So its actual impedance is 0.56, base is 11 square by 30. So it will be 0.1388 pu. So this is the per unit impedance of the 3 generators. Now I need to calculate the per unit impedance of transformers and the transmission line. Now in case of transformer T1, impedance is given as 15.2 ohm on high tension side. High tension means high voltage. Now which side is high voltage for transformer T1? Secondary side is having high voltage. So T1 is 15.2. So base must be taken on the secondary of 1. The secondary of 1 is actually section number 2. Base is 30 by 33. Okay. So we have to take 33 square by 30, which will come out to be 0.4187 pu. For transformer T2, impedance is same 15.2 ohm on high tension side. Now high tension side for second transformer is primary, because the primary voltage is 33. It is higher than the secondary voltage, so it is the high tension side. 33 square by 30, it will yield the same result, 0.4187 pu. Last is my transmission line, 20.5 ohm. Transmission line is lying in section number 2. So it will be simply 20.5 divided by 33 square by 30. So how much will this come out to be? It will be 0.5647 pu. So this way you have to calculate the per unit impedance on suitable base for each and every component in the power system. Then you must interconnect these components to attain the per unit diagram. Like here, this is my generator G1, its per unit reactance. Then this is the per unit reactance of T1. This is your transmission line. This is your T2. This is my G2. This is your G3. Okay. So here we have represented all the components and interconnected them in the base, series and parallel based on the topology given in the problem. Okay. So these are the simple steps that you have to follow to represent the power system in PU. Let us look at another variation of this problem. Here, ratings of different components are given to me, but all the impedances that are already given to me are in per unit. Now, whenever the impedance is given in per unit, it means it is given on its own base. Okay. Now, if it is given in its own base, as I told you earlier, we have to choose a base for the entire power system. So, we will need to transform these impedances to that universal base to derive the equivalent circuit. So, let us first see the circuit. We will divide it into sections based on transformer. This is section number 1, 2 and section number 3. Now, the system base is given as 100 MVA and voltage at G1 is 2400. So, base will be 100 MVA in section 1. Voltage base will be 2400 volt. Now, other bases will be determined based on section number 1. So, power base remains same. So, it will be 100 MVA for all the 3 sections. Now, voltage base will be determined based on the turns ratio. For transformer T1, the voltage transformation ratio is 2400 by 9600. So, secondary voltage will be 9600 by 2400 into 2400, which is 9600 volt. The transformation ratio for T2 is 10 by 5 kV. So it will be 5 by 10. Primary voltage is 96 because the secondary voltage of T1 will be primary voltage of T2. So it is 4800 volt. So now if you see, the base voltage can be different from the rated because the rated secondary voltage of T2 is 5 kilovolt, whereas here the base is 4800 volt. So do not directly go on assuming the rated voltage as the base voltage, it can be different. Now we have bases for all the sections. Let us calculate the PU impedance of all the elements. Now to calculate PU impedance, we have to change the base. So let us first change the base for G1. Z1 or Z, it will be old impedance, that is 0.2 into V old by V new. Given rated voltage is 24, that will be V old. New is the assumed base, which is 2400 volt. Okay, so rating is taken as old base and the assumed base is taken as new base into S new. S new is 100 MVA, given base is 10. 100 by 10. So this will be 2 PU. Similarly, generator G2, it is also lying in section number 1. So base will be 100 MVA, 2400 volt. So it will be 0.2 into, given voltage is 2400, assumed is also 2400. Then given base is 20 kVA, assumed is 100. So this will be 1 PU. Then for the case of transformer T1, we have been given the per unit impedance as, in T1 it is 0.1 PU. Now since this impedance is in PU, we do not need to know the side. Okay, because whenever the impedance is in PU, it is same on primary and the secondary. But remember, when you are transforming the impedance, take the new and the old base on the same side. So let us choose the bases old as well as new on the primary. This is, I am just assuming, so let us take it at primary. So primary old voltage is 2400. New voltage, that is assumed base, is also 2400. Okay. So old is 2400, new is 2400 on primary of T1. Now MVA base chosen is 100 MVA, given it is 100 kVA, it is 40 kVA. So it will be 0.25 PU. For transformer T2 it is 0.1 PU. Now you have to decide where you will take the base, on primary or on the secondary. So let us take on secondary. So here on the secondary, the rated voltage is 5 kV. So old base is 5000. Sorry, this base voltage was 4800. And the assumed base is 4800. New MVA is 100, old is 80. This comes out to be 0.136 PU. Then for the case of transmission line, here the impedance given is in ohms. So we do not need to change the base. This is actual value. We will divide it by the base impedance of section number 2. Section number 2 has the base impedance 9600 square by 100 kVA. So this will come out to be 0.054 plus J 0.217 PU. And the last component that remains is motor. For motor, the impedance given is 0.2 PU and the voltage is 4 kV. But the voltage here is on the motor side 4800. So 0.2 into old voltage is 4000, assumed is 4800. What about the MVA base or the KVA base? Given for the motor is 25 kVA, assumed is 100. So change it as kVA, 100 kVA. So new is 100, old is 25. So how much will this come out to be? It will be 0.2 into 4000 square divided by 4800 square into 4. So it will be 0.55 pu. Now we have to interconnect these components to realize the entire system. So G1 and G2 were connected in parallel. So let me connect them in parallel. Impedance of G1 is 2 pu. For G2 it is 1 pu. So it will be 2, 1. Okay. For then there was transformer T1. T1 has the impedance 0.25 pu. J 0.25. Here also you can place J2, J1. Then transmission line. Transmission line has a real as well as imaginary part. 0.054 J 0.217. Transformer T2 J 0.136. Okay. Then the last component is your motor. J 0.55, and this will be the EMF of motor. This will be generator EMF 1, 2. So that will be the per unit network for the power system. So that is how you construct the per unit network for any power system network. So let us summarize what we learnt in this lecture. We first saw single line diagram. Okay, then we saw equivalent circuit of different components that are connected in a power system. Then we saw that there were large number of loop equations, that is why we cannot use such a equivalent circuit. So we revisited our per unit system. Then we saw how transformer is represented in pu. It is represented just by a series impedance. Then we saw how per unit reactance diagram can be drawn for any power system network. So this is the foundation stone for the fault analysis, because on this only we will build our fault analysis of different power systems. Okay, so this you must perfect it. You must design different power system and then try to design their per unit reactance diagram. If you do it for one or two problems that have been designed by you, it is sufficient, not anything more than that. Okay, in the next lecture we will see a mathematical concept on how to analyze the unbalanced system in terms of balanced components. That we will see in the next lecture. In delta is always 0. If we want to find positive sequence component, it will be 1 by 3. Hi guys, in the last lecture we saw per unit system, which is used for the representation of power system. So we first saw a single line diagram. How is it used to represent the power system? Then we drawn equivalent circuit of the power system. Then we saw per unit reactance diagram. And we observed whenever there is a transformer in PU does not have any turns ratio. Okay. So we can directly represent it by a series impedance that we covered in the last lecture. In this lecture, we will be focusing our attention to the analysis of unbalanced system. So suppose, first of all, what is a balanced system? A system always has two components. One is the source, other is the load. A balanced system is the one which has a balanced source as well as a balanced load. That means the source voltages must be equal in magnitude and phase displaced by 120 degrees, whereas the load impedances must be equal in each phase. Now, when we talk about an unbalanced system, the thing is, in an unbalanced system, either the source can be unbalanced or the load can be unbalanced. Like in this example, if you see, all the voltages have equal magnitude, that is 100. Phase shift is also 120. So source is balanced. But if you see on the load side, one impedance is 10 ohm, 20 ohm and 30. So it is unbalanced. So here the source is balanced whereas the load is unbalanced. Hence it is an example of an unbalanced system. Now to simplify this, we have to apply the KVL. So let us start here. Plus minus, plus minus, plus minus. Similarly plus minus. So VAN minus IA into RA plus IB into RB minus VBN must be 0. Similarly, VBN minus IBRB plus ICRC minus VCN must be 0. Similarly, VCN minus ICRC plus IARA minus VAN must be 0. Now here we have three equations and each equation consists of two currents out of IA, IB and IC. So these equations or IA, IB and IC cannot be solved from a single equation. We have to solve these three equations to derive the three currents. But the benefit in case of a balanced system was we could solve only one phase and then arrive at the result which will be applicable for the other two phases with a phase shift of 120 degrees only. Okay. But that facility is not available in case of an unbalanced system. So we need to devise special methods for the analysis of unbalanced system, and those methods are called as symmetrical components. Okay. So what does symmetrical component means? In symmetrical components, we will break the unbalanced system into a set of balanced phasors and one set of cophasal quantities, and that is precisely the Fortasc theorem. It says in a n-phase unbalanced system, you can break it into n minus 1 set of balanced phasors and one set of cophasal quantities. So in case of 3 phase, it will be 2 and 1. Cophasal quantities means the quantities which will have the same phase. Okay, because in case of balanced, we know there should be a phase shift of 2 pi by n radian or 360 by n degree. So that is the criteria for a balanced, but in cophasal the phase shift should be 0. So that is what your Fortasc theorem tells you. In case of three phase, we will break it into two set of balanced phases and one set of cophasal quantities. So if we can break a system from unbalanced system to a balanced system, then the analysis would be easier, as in case of a balanced system, we will only solve for one phase and other two phases will automatically follow with a phase shift of 120 degrees. Now what is a positive sequence? First of all, the sequence in which R, Y, B, that is red, yellow, blue, or A, B, C, in this manner they are arranged, it is called as a positive sequence. So in terms of phasors, it will be A, then B, then C. So for a balanced system, there are two sequences defined. One is the positive sequence and the other is the negative sequence. For positive sequence, we use the subscript 1. So it will be A1, B1, C1. So magnitude of VA1 must be equal to VB1 must be equal to VC1. Okay. Why magnitude must be equal? Because it is a balanced set of phasors. And the phase shift is 120 degrees, 120 degrees, and 120 degrees. And the sequence is A, then B, then C. Okay, that is your positive sequence. Next set of balanced phasors comes as negative sequence. It will be A, then C, then B, or R, then B, then Y. Then how will my phasor diagram look like? A, then C, then B. If you look clockwise, it will be A, C, B. Now, this phase shift is 120 degree. This is also 120. This is also 120. To differentiate positive and negative sequence, we will represent negative sequence by 2. A2, C2 and B2. Here also, since it is a balanced system, VA2 will be equal to VB2 will be equal to VC2. Okay, since it is a set of balanced phasors. So this is our negative sequence. This is also a set of balanced phasors. Okay, so balanced condition requires a phase shift of 120 degree in three phase. That is true for positive as well as negative sequence. Last is zero sequence. As the name suggests, zero. That means no sequence. No sequence means that all must be lying in the same phase. None is ahead and none is behind. So it will be like A, B, C, and to represent it we will use 0. Here also the magnitudes will be equal, but one additional thing, their directions are also same. There is no phase shift. In zero sequence there is no sequence, hence there is no phase shift. But the first thing that comes to mind is when we have broken into sequences, VA has been broken into VA1, VA2, VA0. Similarly, VB has been broken into VB1, VB2, VB0. VC has been broken into VC1, VC2 and VC0. Now if you see, from 3 quantities I have migrated to 9 quantities. Then the first question that comes to mind is, how does it simplify my analysis? Rather, it is complicating my analysis instead of making it simple. Now I have to deal with 9 quantities. If you were to simplify the analysis, then if the number of variables are not increased, at least it must have been same. It should not have been increased. If you cannot decrease, then at least let it keep the same variable. That means somehow I have to reduce these 9 variables to a set of 3 variables. How to do that is by establishing a relationship between these variables. Now I know in positive sequence as well as in negative sequence, the magnitudes are same. There is just a phase shift of 120 degrees. So we define a phase shift operator to represent that phase shift. So first of all, understand this. E raised to the power j theta represents phase shift of theta anti-clockwise. How? Suppose there is a complex number z r e raised power j gamma. Now you multiply it by j theta. So its angle will become j gamma plus theta. So its angle changes. That means it has rotated by an angle theta. So to apply a phase shift of theta, you will multiply it by j theta. For a phase shift of 120 degree, you will multiply by e raised power j 120 degree, which is called as alpha. It gives 120 degree anti-clockwise rotation. For clockwise, what you will do is e raised power minus j 120, which will be alpha conjugate. It will give 120 degree clockwise rotation. Okay, it can also be written as 360 minus 240, which will be e raised power j 240, that is alpha square. So alpha square gives me a clockwise rotation of 120 degree, and alpha gives me a anti-clockwise rotation of 120 degrees. Okay, so this is called as your phase shift operator. Now let us see how we can apply it to our problem of positive, negative and zero sequence. In positive sequence, I know that VB is lying at 120 degree clockwise from VA. So that means I can write like this: VB1 is alpha square VA1, as it has the same magnitude and a phase shift of 120 degree clockwise. Similarly, VC1 lies at 120 degree anti-clockwise, alpha times VA1. Now, similarly, VB2 in negative sequence, VB lies at 120 degree anti-clockwise to VA1. So, alpha VA2. Similarly, VC2 lies at 120 degree clockwise, alpha square VA2. But in zero sequence, they all have the same phase. So now we can write like this: VA is equal to VA1 plus VA2 plus VA0. Whereas VB can be written as alpha square VA1 alpha VA2 plus VA0. VC can be written as alpha VA1 alpha square VA2 plus VA0. So now I have represented all the three phase voltages in terms of three variables, that is VA0, VA1 and VA2. If we write it in matrix terms, VA, VB, VC. Now I am taking the sequence as VA0, VA1, VA2, that is 0, 1, 2. So VA is VA0 plus VA1 plus VA2, VB is VA0 plus alpha square VA1 alpha VA2, VA0 alpha VA1 alpha square VA2. So this will be V ABC is A V 0 1 2. Okay, and to apply the inverse transformation, that is to derive symmetrical components from the three phase voltages, we will take the inverse. Inverse you can directly remember that we will interchange alpha and alpha square and divide it by 3. Okay, this matrix you can directly memorize: VA, VB and VC. This is the inverse transformation, and as I told you, it is only applicable for a set of phasors. So that means if it is applicable for a set of phasors, so it is only applicable for currents and voltages and not for the case of impedances, because impedances are not phasors, they are just a set of complex quantities. Phasors do have certain frequency and they must rotate with that frequency, but impedances do not rotate. Okay, so that is why same sort of relationship I can write for current also. Same matrices will be applicable. I A B C will be A I 0 1 2 and I 0 1 2 will be A inverse I A B C. Okay, so these relationships are valid for currents as well as voltage. Now If we try to determine zero sequence current will be 1 by 3 IA1 plus 1 by 3 IA plus IB plus IC. Okay. Now, in case of star connection, IA, IB, IC, let us take a neutral here, IN. So, IA plus IB plus IC is equal to IN. So, IA0 is equal to IN by 3. That means IN is equal to 3 times IA0. But if neutral is disconnected, that means IN will be 0. So IA0 will also be 0. There will be no zero sequence current flowing in the circuit. So zero sequence currents can only exist if the neutral is connected to the ground. Otherwise, zero sequence currents cannot flow. Okay. Similarly, if we try to find the zero sequence component in the line voltage, it will be 1 by 3 VAB, VBC, VCA. That is 1 by 3 VA minus VB, VB minus VC, VC minus VA, which is 0. That is no zero sequence in line voltage. Okay. And as I told you in machines also, that zero sequence also corresponds to the third harmonics. Hence, there can be no third harmonic voltages in the line voltage. Okay. Third harmonics can only exist in the phase voltage but not in the line voltage. Now let us try to determine the power in terms of symmetrical component. In a unbalanced system, how will you calculate the power? You will calculate power of each phase individually and then add all the three phases together. Because we cannot multiply by 3, each phase will have a different power. So how it can be represented? VA, VB, VC, IA, IB, IC conjugate. Okay. So this will be your power. So this can be represented as V ABC transpose and I ABC conjugate. Why transpose? Because this matrix is a column vectors and here we have written it as row vector. So we have to take conjugate. Now we know VABC is equal to A times V012. Similarly, IABC will be A times I012. Okay. Now here we have VABC transpose. So if we take transpose of such a matrix, it will be A into V012 transpose AB transpose is B transpose A transpose zero 1 2 transpose into A transpose. Now if I write down the matrix A here, A was 1 1 1 1 alpha square alpha 1 alpha alpha square. Now if you observe A transpose, it will be 1 1 1 1 1 alpha square alpha 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 square, which is equal to A. So A is a symmetrical matrix. What about A conjugate? Now as I told you, alpha conjugate is equal to alpha square. So alpha square conjugate will be alpha and conjugate of a real number is same. Okay. So the equation forming for the power will be V012 transpose A transpose A conjugate I012. Now we have to multiply A transpose with A conjugate. If we multiply A transpose with A conjugate, first row into first column will give me 3. First row into second column, that will give me, so this will here will be 1 alpha square alpha. First row into second column will give me 1 plus alpha square. 1 plus alpha square is always 0. And 1 dot alpha square is 1. So it will give me 0. Then first row into third column, 1 plus alpha square plus alpha, 0. Second row, 1. Second row into first column, 1 plus alpha square plus alpha, 0. Second row into second column, 1 plus alpha cube plus alpha cube. Alpha cube is 1, so it will be 3. Then second row into third column, 1 plus alpha 4 plus alpha square. Now since alpha cube is 1, alpha 4 is alpha into alpha cube, which is equal to alpha. So that will become 1 plus alpha square, which will be 0. Third row into first column, 1 plus alpha square, 0. 1 plus alpha square plus alpha 4, that is again 0. Then 1 plus alpha cube, that is 3. So it is actually 3 times the identity matrix. Okay, A transpose into A conjugate will give me 3 times identity matrix. So power will come out to be 3 times V012 transpose I012 conjugate, that is 3 VA0 IA0 conjugate VA1 IA1 conjugate VA2 IA2 conjugate. Okay, that will be your three-phase power in terms of symmetrical components. So this formula is very important when it comes to the fault analysis. We will use it to find the short circuit MVA. Now let us look at a problem based on the symmetrical components. It is saying a delta connected balanced resistive load is connected across a unbalanced three-phase supply. And I have been given current in line A as 10 angle 30. Current in line B is 15 angle minus 60. But current in line C is unknown. Now the thing is, in case of a delta connection, by means of KCL, I can directly say the total current entering must be equal to leaving, so it must be 0, since all the currents are entering. So IC must be equal to minus of IA plus IB. How much will this come out to be? IC, if you calculate, it will be 18.02 angle 153.69. Okay, so now I know IC. So if you want to find symmetrical component IA 0, that will be 1 by 3 IA plus IB plus IC. Since we know the sum of these three currents is 0, it is 0. So 0 sequence component of line current in delta is always 0. If we want to find positive sequence component, it will be 1 by 3. How much? Then IA plus alpha IB plus alpha square IC. Now one trick that what you can do here is, IA is 10 angle 30. This is IB. Then alpha is 1 angle 120, that is e raised power j 120. IB is 15 angle minus 60. Then in alpha square, instead of taking 1 angle minus 120, take 1 angle 240. And the value is 18.02 angle 153.69. So this will come out to be 14 angle 42 degree ampere. Now when you wish to calculate IA2, then what you will do is you will take alpha square here and alpha here. So in the calculator, just the only thing that you need to do is take 240 here and take 120. You can edit the equation there itself. But if you would have taken minus 120, then you cannot convert 120 to minus 120 because you cannot increase the number of digit. Because in 120 there are only 3 digits. But in minus 120, due to a negative sign, there are 4 digits. So you will have to rewrite the equation entirely again. But if you use 240, you can change it to 120. So this component will come out to be 4.66 angle minus 111.75 degree ampere. So that will be your negative sequence component. So here in this chapter, what you need to do is, in this topic, you need to remember the matrices A and A inverse. Those are very important. So let us summarize what we covered. We first saw an example of unbalanced system. Okay. Then we saw the Fortesque theorem, which enables us to identify or break the unbalanced system into balanced system. Then we saw positive, negative and zero sequence. Then we learnt about the phase shift operator alpha, that 1 plus alpha square is 0. Alpha cube is 1. Alpha conjugate is alpha square. Alpha square conjugate is alpha. Then we derive the matrices A, 1, 1, 1, 1 alpha square alpha, 1 alpha, alpha square, which is same as A transpose. And we saw A inverse, which was 1 by 3, just 1, 1, 1, then 1 alpha, alpha square, 1 alpha square, alpha. Okay. So this is what we covered in this lecture. And we saw there is the line component, the zero sequence component in the line current is equal to the neutral current. If the neutral is disconnected, it will be 0. Okay. And we saw zero sequence component of line voltage is always 0. In the next lecture, we will see how does this dividing the components or dividing the voltages and current into different sequences, how does it impact our equivalent circuit of each component. That we will cover in the next lecture. Lecture we covered the concept of symmetrical. Hi guys, in the last lecture we covered the concept of symmetrical components. There we saw to analyze an unbalanced system, it is very difficult as each KVL equation involves more than one current. So we cannot separate out the current in terms of different equations. We have to solve all the equations simultaneously to arrive at the result. So we saw a theorem called as Fortesque theorem, which enables us to break the unbalanced system into a set of balanced phasors and one set of cophasal quantities. So in that way, I can analyze the balanced system much more easier because I have to analyze only a single phase and rest of the phases can be calculated directly by 120 degree phase shift. Okay. So in there, we saw that it can be broken into three sequences: positive sequence, negative sequence and zero sequence. Zero sequence means cophasal quantities, that is they are having the same phase. So we saw that we saw the phase shift operator, which enabled us to write different phases of a same sequence in terms of a single variable. So we saw that 1 plus alpha square would be 0. Alpha cube would be 1. Alpha square conjugate would be alpha. Then we saw that convert between the phases and the sequences, we can use the matrix 1 1 1 1 alpha square alpha 1 alpha alpha square V0 V1 V2. And to derive the sequence components or symmetrical components from the phase voltages, we can use the inverse of this matrix, which is 1 by 3, and we replaced alpha by alpha square VA VB VC. Okay, and we saw that line component 0 sequence is equal to IN by 3, and line voltage 0 sequence component is always 0. That we covered in the last lecture. So in this lecture we will focus our attention to how to design the circuits or equivalent circuit for different sequences, that is for positive sequence, negative sequence and 0 sequence. How to design different circuits, each for a different sequence. So let us first start with a star connected winding. In this star connected winding we have the neutral grounded by a impedance Zn. In A phase current is IA, IB and IC. Now why I am considering a star connected winding is because a winding concept can be taken directly to a alternator where there will be winding, and as well as a transformer, there will be windings. So hence first of all we are considering a star connected winding. Here current IA will have three components, IA0, IA1 and IA2. Similarly, IB will have three components, IB0, IB1 and IB2. Here I am assuming that the currents are unbalanced, IC0, IC1 and IC2. So this way there will be three components in all the currents. Now if we calculate IN, that is the neutral current, will be equal to IA plus IB plus IC, and as we derived in the last lecture, this is equal to 3 times IA0. That is only 0 sequence current will flow through the neutral. Now let us consider one by one each sequence, that is positive, negative and 0 sequence, to understand how you can draw the equivalent circuit. First of all, positive sequence network. For positive sequence, I have only shown the positive sequence current flowing in the windings, that is IA1, IB1 and IC1. So I have neglected the negative and the 0 sequence component. Now by KCL, neutral current IA1 plus IB1 plus IC1 must be 0 because the balance sum will be 0. That means neutral voltage, which is minus IN into Zn. Why minus? Because neutral current will be flowing like this, so it will be plus minus. So this will be 0. Now if we wish to calculate the voltage here, VA1 will be equal to minus IA1 into Z1, because plus minus will be like this. Okay. So how can I represent this in the circuit form? This is represented as a reference bus that is having a 0 potential. Then this is the positive sequence impedance Z1. Current is IA1. Now this will be VA1. Here it will be plus minus. So VA1 will be minus IA1 into Z1. Now what is this Z1? What is the positive sequence impedance? This we will see when we will start considering the alternators and the transformers. Then you will easily understand what is meant by the positive, negative and 0 sequence impedances. Because up till now what we have seen is just the positive sequence voltages and currents. Never we have talked about the impedance. And I only told you that Fortes theorem can only be applied to voltages and current and not the impedances. Then how come this impedance is arising, which is a positive sequence impedance? Physical significance we will see with regards to the different components of the power system. Next is the negative sequence network. Similarly, in negative sequence, I have considered only the negative sequence currents, that is IA2, IB2 and IC2. Now in this case the neutral current will be IA2 plus IB2 plus IC2, which will be 0. Okay, that means the neutral voltage again, which is equal to minus IN into Zn, will be 0. If we apply KVL, VA2 will be equal to minus IA2 into Z2, because plus minus will be here. Here Z2 is the negative sequence impedance. To represent this as a circuit, this is reference bus, this is Z2, this is IA2. So it is VA2. VA2 is minus IA2 into Z2 plus minus. Okay. So that is how we can draw the negative sequence network. Now let us proceed to the most interesting part, that is the zero sequence network. Here I have only shown the zero sequence current IA0, IB0 and IC0. Now here the neutral current, which will be equal to IA0 plus IB0 plus IC0, which will be equal to 3 times IA0. That means the neutral voltage, which is minus IN into Zn, will be minus 3 IA0 into Zn. Hence, if we apply KVL, Vn minus IA0 into Z0. Earlier Vn was 0, so I was directly writing minus IA1 into Z1 or minus IA2 into Z2. Minus 3 IA0 Zn minus IA0 Z0. Now if we combine these two terms, I can write minus IA0 Z0 plus 3Zn. So neutral impedance appears as 3 times the neutral impedance in the zero sequence network. So how will my circuit look like? This will be the reference bus. This will be 3Zn, Z0, that is VA0, IA0. Okay. So that is how we can draw the zero sequence network from a star connected winding. Now here we were considering Zn. So there is a chance that Zn may not be connected to the ground, it may be isolated. So if Zn is isolated, that is, it will not be connected to ground, so Zn can be taken as infinity. So the zero sequence network will be affected. It will be shown as open circuit. Okay, because there is no current. Now this means no zero sequence current can flow. And anyways it is true, if we do not connect the neutral, no zero sequence current can exist. And this is pretty much visible from the zero sequence network. Okay. Now suppose if Zn is, or the neutral is, solidly grounded. Solid grounding means that Zn is 0. Zn will be taken as 0. So the circuit will be Z0, then it will be shorted. So VA0 will be minus IA0 into Z0. Zn will be taken as 0. So these are the two extreme cases in which neutral is not connected to ground or the neutral is directly connected to ground. That is why I was taking Zn initially, because then we can derive these two cases directly. So this was all about your star connected network. Now let us consider the delta connected winding. If the winding is delta connected, then this is the zero sequence current IAB0, IBC0, ICA0. Now I know zero sequence components are all equal. Okay. So these are all equal. So it is flowing like this. Now if I want to calculate IA0, that is the zero sequence component in line current, by KCL I can write it as ICA0 minus IAB0, which will be 0. So there is no zero sequence current in the line, but zero sequence current can easily exist in the phase. So how to represent this fact that zero sequence current can exist in the phase but not in the line? What we will do is, we will take reference bus. This will be Z0 and it will be connected to the reference bus. And this line will be shown open here. That is, zero sequence current cannot enter the line, but it can keep on circulating in the phase. Though this circuit might not look practically correct to you, but it is just a representation to indicate that zero sequence current can exist in the phase but not in the line. Okay. So that is how we draw the delta connected zero sequence network. And positive and negative sequence network will remain same because they are not dependent on the neutral grounding. So these are general concepts for the star and the delta connected winding, how we draw the zero sequence circuits or the positive, negative and zero sequence network. Now let us proceed to the first component of the power system, which is a alternator. So first case we are taking for the star connected alternator. Now here we have shown three EMF, EA, EB and EC, and the neutral is grounded by impedance Zn. Now in case of a star connected alternator, let me first show you the schematic of alternator. This will be A phase, this will be B phase, this will be C phase. Now we know whenever the prime mover or whenever the rotor lies along any phase, maximum EMF will be induced in that phase. Now, if rotor is lying along this, then maximum EMF will be induced in A. Then when the rotor moves by 120 degree, then maximum EMF will be induced in B. And then when it again moves by 120 degree, maximum EMF will be induced in C. That means the order of maximum EMF will always be A, then B, then C. And they will automatically be displaced by 120 degrees. Why? Because they have the space displacement of 120 degree. Until you change the direction of rotation of the rotor, the sequence of maximum EMF will always be A, B and C, which is my positive sequence. So this statement I mentioned something like this, that only the EMF can have positive sequence, it cannot have negative sequence or the zero sequence. Why? Because until and unless you change the direction of rotor rotation, it will go from A, then B, then C. If it goes in the order of A, B, C, that means it is inducing positive sequence EMF. So keep this in mind. EMF can only have positive sequence, it cannot have negative or the zero sequence. That is, when we will be drawing the circuit, EMF will only appear in the positive sequence network and not the negative or the zero sequence network. Now let us first consider positive sequence. What is the meaning of positive sequence with regards to alternator? In alternator, we study that three-phase voltages or current induce rotating magnetic field. Okay. If they are inducing rotating magnetic fields, then what will happen is, the rotating magnetic field will rotate at a speed ns. In case of positive sequence, it rotates in same direction as rotor. Okay. If it rotates in the same direction as the rotor, that means rotor is rotating at ns. Magnetic field is also rotating at ns and both are in the same direction. So relative speed becomes 0. Now one thing that you must clearly understand about the faults, suppose this is EMF, this is J-axis. Suppose a short circuit occurs here. Then the current IA1, if we find, or let us say IA, IA will be EF angle delta by J axis. So that is EF by axis angle delta minus 90. That it is 90 degree lagging, or we can say 0 power factor lagging. Now in a synchronous machine, if the current has a 0 power factor lagging, then what happens to the armature reaction? This is our field MMF. This is our induced EMF. Current is 90 degree lagging. So this is armature reaction, which is demagnetizing. Now in case of fault, since armature reaction will always be demagnetizing, there will be no problem of saturation. So under short circuit, the machine cannot saturate. But how do we represent the axis? This is D axis. This is my Q axis. So under short circuit condition, FAR or IA lies along D axis. Okay, it always lies along D axis. So the air gap or the reluctance that it will be offered will be corresponding to the D axis air gap. So the reactance that will be offered, armature reaction, will be XAD. Okay. So the reactance that it will encounter is leakage plus XAD, which is equal to XD. Now the one beautiful thing about this concept is, since it is a positive sequence, both are rotating at the same speed. That is, field MMF is rotating at a speed ns, and armature reaction also rotates at a speed ns. So it will always, they will always have a difference of 180 degree. So it will always lie along the D axis. Hence it will always be offered a reactance of XD. Thus positive sequence reactance is equal to direct axis reactance for the case of synchronous machine. Okay. But this further is divided into three categories, which I will explain later on how we define that three categories. First is XD double dash, which is subtransient reactance. XD dash, which is transient reactance. XD, which is steady state. Okay. So these are based on different times. Subtransient means in the initial 1 to 2 cycle after the fault. This is 3 to 5 cycle after the fault. It is greater than 5 cycles. Okay. So I hope now you understood the concept why we will be taking the positive sequence equal to direct axis. Because in case of faulty condition, fault will have 0 power factor lagging. If fault has a 0 power factor lagging, then the armature current will lie along the D axis. If armature current lies along the D axis, then it will encounter the D axis reactance or the synchronizing or the D axis armature reaction. Okay. So hence positive sequence reactance is equal to XD. In case of negative sequence, what will happen? If current is negative sequence, then rotating magnetic field rotates at ns opposite to rotor. Now rotor has a speed ns. Rotating magnetic field also has ns, but they are in opposite directions. So relative speed will be equal to 2ns. Okay. So now if we see in terms of phasor diagram, this is my field MMF, this is EMF, this is IA, but now it is rotating at ns like this. This is rotating at ns like this. What we can do instead is, we can assume that this has the 0 speed and this rotates at 2ns with the relative speed. Now if it rotates at 2ns, right now it is lying along D axis. But after 90 degree rotation, it will lie along q axis, then again along D, then again Q, then again D. So it will alternatively lie along the D axis and Q axis because it is rotating with respect to the field MMF or with respect to the rotor axis. So it will sometime lie along the rotor axis and at other time it will lie perpendicular to the rotor axis. So it will encounter the D axis reactance as well as Q axis reactance alternatively. For half the time period it will have D axis reactance, for half the time period it will have Q axis reactance. That means the reactance that it encounters is dependent on time. At some time it is XD, at other time it is XQ. Then how to use some reactance? The best way out of it is take the average of the two. That is XD plus XQ by 2. Now I know XQ in case of salient pole generator is always less than XD because it has larger air gap as compared to XD. So that means X2 will be less than XD plus XD by 2, which is equal to XD. So X2 is less than X1. That is, negative sequence reactance is always less than positive sequence reactance. Okay. The difference in positive and negative sequence is, in negative sequence the rotating magnetic field rotates opposite to the rotor, hence it encounters positive and negative sequence, it encounters D axis and Q axis alternatively, whereas in positive sequence it rotates in the same direction, hence its relative position with respect to field MMF is fixed. Okay, so it always encounters D axis. Okay, it never encounters Q axis. Is it fine? So that is why in case of negative sequence we will take average of D and Q, whereas in positive sequence we will only take D axis. In case of zero sequence, what happens? In case of zero sequence, since there is no phase shift, that means there is no rotating magnetic field. Now in case of alternator, how my windings are arranged? This is A dash, B dash, C dash. That means axis of A is upwards. Okay, perpendicular to this. Then axis of B will be at 120 degrees to this. That is FB. Axis of C will lie along this. Now, since all are having the same phase, FA will be equal to FM sin omega t. FB will be equal to FM sin omega t. FC will be equal to FM sin omega t. Since all are having the same phase, they will have same magnitude at each and every time. So their resultant will become 0. Three vectors oriented at 120 degrees with respect to each other having equal magnitude will yield a 0 resultant. It is similar to your phase shift operator. 1 alpha square. 1 plus alpha square is always 0. Similarly here, FA0 plus FB0 plus FC0 will always be 0. Okay. So, since the sum is 0, it does not create any rotating magnetic field. It only encounters the leakage reactance. Okay, there is no armature reaction. Net flux is 0. So, armature reaction will not be present because armature reaction is created due to the net flux produced by the rotating magnetic field. But here there is no rotating magnetic field. The net flux is 0. So, there is no armature reaction. Only reactance is XL. So, X0 will be equal to XL. Okay. So, here we saw that X1 is greater than X2. It will again be greater than X0. Because X1 and X2 also had the armature reaction component, but X0 only has the leakage reactance. So, this is the physical significance of the positive, negative and zero sequence reactances of the alternator. Positive sequence is equal to direct axis because fault power factor is 0 lagging, armature current always lies along the d-axis, and there is no relative motion, so it will encounter d-axis reactance. In case of negative sequence, the MMF rotates at 2 times ns with respect to field, so it encounters d-axis and q-axis alternatively, and hence we take the average of the two. In case of zero sequence, no rotating magnetic field is formed and net flux is zero, so no armature reaction, only leakage component is considered. Now what happens for the case of delta connected alternator? Now in case of delta connected alternator, the problem will be we can draw the circuit, but there is no reference bus as there is no neutral. So we have to convert it to star. Here we will take the EMF EA by root 3, EA by root 3, EA by root 3, because if line voltage is EA, phase will be EA by root 3. And while converting from delta to star, the impedances will become Z1 by 3. Now in case of star, positive sequence would be reference bus EA Z1. This is IA1. So this is VA1, which will be equal to EA1 minus IA1 into Z1. But what to do in case of delta? In case of delta, what we will do is we will divide it by root 3, divide this by 3. So VA1 will be EA1 by root 3 minus IA1 Z1 by 3. This is your star connection. Sorry, this is your delta connection, positive sequence network. What happens for the case of negative sequence? In case of star, since there is no EMF in the negative sequence or the zero sequence, we will just place the impedance. This will be IA2. So VA2. VA2 will be equal to minus IA2 into Z2. But in case of delta, what you will do is you will divide it by 3. So it will be IA2 Z2 by 3. Similarly, in case of zero sequence, in case of star, what will happen? There will be no EMF, just the zero sequence impedance Z0, plus we will have 3 times the neutral impedance as we derived for the star connected winding, like this. So VA0 will be minus IA0 Z0 plus 3Zn. Okay. But in case of delta connection, there is no neutral grounding, so this will be taken as open circuited. That means IA0 will be equal to 0. Zero sequence current cannot flow in the lines of the delta connection. So that is how you will draw the equivalent circuits or the sequence networks for the case of positive, negative and zero sequence in case of star and delta connected alternators. Okay. So here let me summarize. Star, delta. In case of star, how does my positive sequence network looks like? EA, Z1, IA1, VA1. In case of delta, how does it look like? EA by root 3, then Z1 by 3, IA1, VA1. In case of negative, we will remove the EMF because EMF is always positive sequence Z2, IA2, VA2. Here we will have Z2 by 3, IA2, VA2. Okay. And in case of zero sequence, we will have Z0, 3Zn, IA0, VA0. Here we will have Z0, but it will be open circuit, no neutral impedance. Sorry, this will be Z0. So IA0 will be 0. So these are the sequence networks for the case of alternators, both star and delta connected. So let us summarize what we covered in this lecture. We first saw the star connected winding, the sequence network for star connected winding. Here one important thing that you must remember, in zero sequence neutral impedance appears as 3Zn. Then we saw delta connected winding. Here we saw zero sequence current can exist in phase but not in the lines of the delta connection. Then we saw star connected alternator, and the first thing that we observed was EMF can only have positive sequence, it cannot have negative or the zero sequence. Why? Because it depends on the direction of rotor rotation. If rotation is fixed, then negative and zero sequence cannot be induced. Okay, so EMF is always positive sequence. Then we saw positive sequence impedance was equal to XD because armature current was always lying along the D axis as the fault power factor was 0 lagging. Then we saw negative was equal to XD plus XQ by 2 because field was rotating at a speed of 2ns with respect to field MMF. Hence, it will encounter D axis and Q axis alternatively. In case of zero sequence, no rotating magnetic field was present, so it was equal to XL. In delta connection, what we saw is we have to take EMF as EA by root 3 and reactance as Z1 by 3. Because we will convert delta to star before drawing the circuit. In the next lecture, we will continue drawing the sequence networks for the other components in the power system, that is your transformers and the transmission line, to know how to draw the sequence networks for the entire power system. That we will cover in next lecture. Hello guys, in the last lecture we started with the sequence networks. So we saw that for different sequence components we designed different circuits. So first we looked at the case of a star connected winding. There we made an important observation that neutral impedance does not appear in the positive and the negative sequence network but only appears in the zero sequence network. And in zero sequence network it appears as 3 times Zn. Then we looked at delta connected winding and we observed that zero sequence currents can exist in phase but not in line. So what we did is we connected the winding to the reference bus and kept the line open circuit to indicate that there are no zero sequence currents in the line. Then we looked at the case of alternator. And the first observation that we made is, as long as the direction of rotation of the rotor is same, the induced EMF will be positive sequence, that is EA, EB, EC. Then we saw the positive sequence network and observed that since fault current is 0 power factor lagging, it will lie along the D axis and it also rotates at the synchronous speed in the direction of rotation of the rotor. So the relative distance between the rotor or the field axis and the armature MMF does not change and it always lies along the D axis. So we kept x1 is equal to xd. Then for the negative sequence network, the armature MMF rotates at synchronous speed but in a direction opposite to the rotor direction. So there is a relative speed of 2ns between the rotor MMF and the armature MMF, and hence it encounters xd and xq in an alternate fashion. So we kept x2 is equal to xd plus xq by 2. Then we saw zero sequence network. There we saw that all the three MMFs were equal and aligned at 120 degree with respect to each other. So their resultant was 0 and hence they did not produce any armature reaction. So zero sequence reactance came out to be equal to leakage. And we saw the order was x1 was greater than x2 was greater than x0. This was the order of the sequence impedances of a alternator. In this lecture, we will concentrate on deriving the sequence networks for the case of transformer and the transmission line. So let us first start with the transformer. In case of a transformer, what happens is the equivalent circuit is something like this. If I have referred the entire circuit to primary, it will be something like this. This will be core loss resistance, magnetizing reactance, then winding resistance and leakage reactance. Now the current flowing in the shunt branch is called as no load current. And for the case of power transformer, it is almost 1% of full load current. And since we are drawing the sequence network to analyze the fault case, so fault current will be 10 to 20 times higher than the full load current. So we can neglect I0. Okay, that means we will disconnect the shunt branch. And as I told you, we have to neglect each and every component that makes the system stable. So resistance will improve the system stability in case of a fault. So resistance will also be neglected. So what we will have is, we will have a series reactance which is equal to leakage reactance. Hence, the positive and the negative sequence networks will be identical. They will just consist of a leakage reactance. Now, why positive and negative are identical? Because here there is no rotating magnetic field. Hence, the positive and negative are not affected by the sequence of the current. So, ZT1 will be equal to XL. And ZT2, that is the negative sequence impedance, is also equal to JXL. This will be IA2. But the case of zero sequence current, as I told you, as we derived, zero sequence current can only flow in the lines of the star connection with grounded neutral, or zero sequence currents can flow in the delta winding phase but not in the line. We derived that the line current can only contain zero sequence component in case the connection is star with a grounded neutral. Otherwise, it can only exist in phase of the delta. That means presence of the zero sequence currents depend on the connection of the transformer. So we have to judge, or the circuit will change based on the different type of connections of the transformer. So the universal circuit that we use for zero sequence network is this. Here we have two series switches. Let me name it as S1, S2, and two shunt switches S3, S4. Now S1 and S2 series switches indicate that the zero sequence current will flow in the line. That can only happen with star with grounded neutral. S3 and S4 will connect the impedance to the reference bus, and that we did in case of a delta connection. How did I show the presence of zero sequence current in phase? I connected the impedance to the reference bus. So they indicate delta connection. Okay. So whenever any winding is delta connected, we will operate S3 and S4. If it is star connected, we will operate S1 and S2. Now let us see one by one how we will design the circuit for the different cases of, or different connection of transformer. First, let us take the case of star-star connection. Suppose we have star with ungrounded neutral, star with ungrounded neutral. That means star neutral is not grounded on either side. That means zero sequence current cannot flow on the primary as well as on the secondary. Since it is star connection, we will have to operate series switch. For this one, we will operate S1. For this one, S2. but S1 and S2 will be kept open because ground neutral is ungrounded. So this will be the zero sequence circuit of a star-star connection with a ungrounded neutral. Now as this circuit is open circuited, zero sequence current is 0, which shall be the case because there is no neutral grounding, hence zero sequence current cannot flow. Now suppose if I ground this neutral, then this point here will be shorted. Okay, but still since this circuit is incomplete, IA0 will still be 0. IA0 can only flow if this circuit gets closed on both the sides. That is, if I ground on both the sides, then zero sequence currents can exist and this will be shorted. Then IA0 will not be 0. Okay. So, one thing that you must always remember, either the zero sequence current will exist on both sides of the transformer or it will not exist on any side, because in transformer currents are related by the turns ratio. Either the current will be present on both sides or it will not be present on any side of the transformer. Hence we must ground both the sides of the transformer in order for the zero sequence current to flow. You cannot just ground one side and expect the zero sequence current to exist, because that will violate the transformer principle. Now let us generalize this case by placing the neutral impedance. Let me place a neutral impedance here, Z capital N, Z small n. Why I am using uppercase and lowercase? Because primary is represented in uppercase, secondary in lowercase. Now we studied in zero sequence circuit, the neutral impedance appears as 3 times the neutral impedance. So how would the circuit will look like? 3Zn, then transformer zero sequence impedance, which is equal to actually JXL, then 3Z small n, and it will be like this. This current will be IA0. Now you can take the two extreme cases. Zn is equal to 0, which means solid grounding, and Zn is equal to infinity, which is the case of isolated neutral. So all the cases can be derived from this two special cases of the neutral grounding. Hence we have taken a general case in which the neutral is grounded by means of a impedance. Okay. So you can either equate Zn to be 0, infinity, and Z small n and Z small n to be 0 and infinity. That way you can realize all the cases that we have done so far. So this is about the star-star connection. And remember, for star-star connection, we will not operate any of the shunt switch. Next comes the star-delta connection. Primary is star, we will operate S1. Secondary is delta, we will operate S4. Okay, that is a shunt switch. This is my series switch. Now first take the case when Z star is ungrounded and this is delta. Since the star is ungrounded, we will keep series switch open. Since delta is there, we will short the shunt switch. But now since the connection is open, IA0 will be 0. There will be no zero sequence current flowing in the lines of the transformer. Now suppose I ground this, then what will happen? This will be the case. So zero sequence current will flow like this. That is, zero sequence current can exist in the lines of the star connection and in the phase of delta. This you have to disconnect here because series switch is not operated. Okay. So here the zero sequence current cannot exist on the lines of the delta side, but it can flow in the line as well as phase on the star side. How? Because if any current exists in the phase of star, it will exist in the line of star, because in star connection line current is same as the phase current. So here zero sequence current will flow in phase as well as line of star, but only in the phase of delta. So let us again generalize this by placing a neutral impedance, that is Z capital N. So what changes we will do in the circuit? we will show it like this 3Zn. Okay, so this is the equivalent circuit or the general circuit for the case of star delta connection. Next, let us consider the delta star. Now primary is delta connected, we will operate S3 here. Secondary star connected, we will operate S2 here. Okay, this is my shunt switch. This is your series switch. Again, first let us consider the case of delta star ungrounded. Since primary is delta, we will operate shunt switch. Secondary is star, we will operate series switch. But since it is ungrounded, we will keep it open. So here zero sequence current on both the sides of the transformer will be 0. Okay. Now suppose if we ground this neutral, then this switch will be shorted. Then zero sequence current can flow like this. That is, zero sequence current can exist in phase as well as line of the star connection and the phase of delta. Here zero sequence current will be 0. To generalize this, we will place a neutral impedance on the secondary. This will be shown in the circuit in terms of 3 times the neutral impedance, like this. Okay. So that is the equivalent circuit for the delta star connection. Last, let us consider the delta delta connection. Here primary is delta, operate S2, S3. Secondary is delta, operate S4. Both are my shunt switch. So how we will draw the equivalent circuit? We will operate the shunt switch on primary, shunt switch on secondary. Okay, that means zero sequence current can flow in the loop, which indicates zero sequence current can flow in the phase of both primary and secondary, but it cannot go in the lines of either primary or secondary. So these zero sequence circuits are pretty important for the course, because sometimes a zero sequence circuit will be given to you and you will have to identify the transformer connection. In other cases, you may be asked zero sequence circuit given the transformer connection. So zero sequence circuit of the transformer is the most important topic in the sequence networks. Next, let us consider the case of transmission line. In case of transmission line, we will define two types of impedances, ZAA, ZBB and ZCC. This is one category, that is impedance of A due to A, impedance of B due to B, impedance of C due to C. Similarly, ZAB, that is impedance of A due to B, ZBC, impedance of B due to C, impedance of C due to A, ZCA. Okay, so these three will be mutual and these three will be self. Now we studied in case of transmission lines that in case of symmetrical configuration, all inductances were equal, but in case of asymmetrical, inductances were unequal. Okay, so what we did to make the inductances equal? We made the lines as transposed. So if lines were transposed, then I can say that ZAA equal to ZBB equal to ZCC, which will be equal to ZS. Similarly, ZAB is equal to ZBC is equal to ZCA, which is equal to Zm. Okay, so we will give them single values in case of a transposed transmission line. Now let us write the KVL equation for these transmission lines. For the phase A, VA minus VA dash will be ZS into IA plus Zm into IB plus Zm into IC. That is, the voltage drop will be due to all the three phase currents. VB minus VB dash will be Zm IA plus Zs IB plus Zm IC. VC minus VC dash will be equal to ZMIA, ZMIB plus ZSIC. Now the problem with these equations is that if you see, the voltage in A phase is dependent on current in B phase as well as C phase. So these equations are coupled. These equations are not independent. So if I break it into the sequence components, I will have to see whether or not they become independent. So let me write these equations in matrix form. Delta VA, delta VB, delta VC will be equal to ZS, ZM, 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 ZS, ZM, 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 ZS, IA, IB, IC. Okay. Now we know VABC is equal to A times V012. Similarly, IABC is equal to A times I012. So that means I can write it like this. A times delta V012 is equal to Z matrix into A times I012. That means delta V012 will be A inverse Z A I012. So this whole matrix will be the impedance matrix for the sequenced components. So let us calculate this matrix. So first let us calculate Z multiplied by A. If we multiply it by A was 1, 1, 1, 1 alpha square alpha, 1 alpha, alpha square. Now first row into first column will give me ZS plus 2ZM. ZS plus alpha square ZM plus alpha ZM. Now we know 1 plus alpha square is 0. So alpha plus alpha square is minus 1. So the next term would be ZS minus ZM. Next, if we multiply first row by the third column, we will get ZS plus alpha ZM plus alpha square ZM. That is ZS minus ZM. Then second row into first column, we will again get ZS plus 2ZM. Then ZM plus alpha square ZS plus alpha ZM. That is alpha square ZS minus ZM, because 1 plus alpha will be equal to minus alpha square. Then Zm plus alpha Zs plus alpha square Zm. That will be alpha Zs minus Zm. The next term will again be Zs plus 2Zm. Then Zm plus alpha square Zm plus alpha Zs. That is alpha Zs minus Zm. And last alpha square Zs minus Zm. Now this matrix needs to be multiplied by A inverse. A inverse was 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. Okay. Now if we multiply this, what we will get is 1 by 3. First row into first column will give me 3 times Zs plus 2Zm. Then first row into second column will be Zs minus Zm multiplied by 1 plus alpha square plus alpha. That is 0. Then first row into third column will be Zs minus Zm multiplied by 1 plus alpha square, again 0. Then next, second row into first column, Zs plus 2Zm multiplied by 1 plus alpha square, that is 0. Then 1 into Zs minus Zm, alpha cube into Zs minus Zm, alpha cube into Zs minus Zm. Alpha cube is 1, so it will be 3 times Zs minus Zm. Then 1 into Zs minus Zm, alpha into alpha will be alpha square Zs minus Zm. Alpha square into alpha square will be alpha 4, which is alpha. So it becomes 1 alpha square alpha, it will be 0. Then Zs plus Zm into 1 plus alpha square plus alpha, that is 0. Then 1 into Zs minus Zm, alpha raised to the power 4 into Zs minus Zm, that is alpha Zs minus Zm, alpha square Zs minus Zm, 0. Then 1 into Zs minus Zm, alpha cube into Zs minus Zm, alpha cube into Zs minus Zm, that is 3 times Zs minus Zm. Now this 3 can be taken out common. So this matrix will become delta V0, 1, 2 Zs plus 2Zm 0, 0 Zs minus Zm 0. So now if you see the off diagonal terms which represented mutual impedances are gone and only the diagonal terms remain. That is, we have removed the mutual coupling between the equations. So we can directly write delta VA0 is Zs plus 2Zm into Ia0. Delta VA1 is Zs minus Zm Ia1. Delta VA2 will be Zs minus Zm Ia2. So how will the sequence network look like? In positive sequence we will have VA1 dash, here we will have Z1 is equal to Zs minus Zm. Then negative sequence will have VA2 dash Z2, which is also equal to Zs minus Zm. Then zero sequence will have VA0 dash Z0 will be Zs plus 2Zm. So here Z1 is equal to Z2 and Z0 is typically 3 times the Z1. Okay, so that is the relation between sequence impedances of a transmission line. And in case of generator, what we saw, Z1 was greater than Z2 was greater than Z0. In case of transformer, Z1 was equal to Z2 was equal to Z0. In case of transmission line, Z1 is equal to Z0, Z2 and Z0 is 3 times Z1. So that is how, if you are given the same sequence impedances, you can identify the component of the power system. Now let us understand it with the help of a problem. A 25 MVA 11 kV 3-phase synchronous generator has a sub-transient reactance of 20%. So generator reactance is 0.2 pu. The generator supplies 2 motors over a transmission line with transformer at both ends, having rated MVA of 15 MVA, 7.5 MVA, both 10 kV with 0.25 subtransient reactance. Sorry, this is it is talking about the motors. So this is 15 MVA, 7.5 MVA, 10 kV, 10 kV, and both have 0.25 pu subtransient reactance. Both transformers have 30 MVA. Okay, 10.8 by 121. So this must be 121 by 10.8. Delta star with leakage reactance 10%. So 0.1 pu, 0.1 pu. Series reactance of line is 100 ohm. Now we have to draw all the sequence network assuming equal positive, negative and zero sequence impedances of components. Okay. So the first thing that we need to do is we will divide the power system into sections based on the transformer. Then we have to assume the base. Now let us assume the base same as the generator, that is 25 MVA 11 kV. What will be the base voltage in the transmission line? It will be in section number 2 121 by 10.8 into 11, which is 123.24. And what will be in the section number 3? In section number 3 it will be 123.24 into 10.8 by 121, which will come out to be 11 kV. Now we have got the base for each and every section. Let us determine the value of PU reactances of each and every component. For generator 1, old reactance is 0.2, old voltage is 11, new base is also 11, old MVA, new MVA is 25, old is also 25. So this will be J.2. For transformer T1, the reactance that is given to me in the problem is 10%, rating is 30 MVA 10.8 kV. So we have to assume on one side either the primary or the secondary. I am assuming on the primary. Given voltage was 10.8, assumed is 11. Assumed base is 25 MVA, given was 30. So how much will this come out? J 0.0805. Transformer T2 J.1. Let us take on the primary of this. Given voltage is 121, assumed is 123.24. Given base is 30, assumed is 25. So this will be same 0.0805. For the case of transmission line, reactance given is 100 ohm. We will divide it by base. Base will be V square by S. 123.24 square by S is 25. So this will come out to be J.164 PU. For the case of motor 1, what is the rating given to me? 15 MVA, 10 kV, 25% reactance. So J.25, 10 kV was given, we have assumed 11. Then 15 was given, we have assumed 25. So how much will this come out to be? J.3443. For motor number 2, PU impedance is same. Voltage rating is also same. Just MVA is given to me 7.5. So it will be double of this, that is J.6887. Okay, why double? Because the denominator is halved. Now let us draw this in terms of sequence network. First let us consider positive sequence. So let me take a reference bus. Then we will take generator EMF, generator reactance. Generator reactance is how much? J.2. Then there will be transformer. For positive sequence, transformer is represented by impedance. Then transmission line. Then again transformer. Then there are two motors connected in parallel. So motor has equivalent circuit same as that of a generator. So how much reactance? J.34 and J.68. This is generator EMF, this is motor 1, this is motor 2. So this is the positive sequence network. Now in the problem they have said assume equal positive, negative and zero sequence reactances. That means negative sequence impedances will remain same as positive sequence. But what is the essential difference between positive and negative sequence network is that there are no induced EMF in the negative sequence network. So for drawing negative sequence, what we will do is we will remove these EMFs. Okay, so we will directly connect like this. This will be my negative sequence network. There will be no EMFs, the rest will remain same. If we were given separately negative sequence impedances, then we will replace positive sequence impedances by negative sequence. Now to draw zero sequence network, we have to consider the transformer connections also. Okay, because zero sequence network depends on transformer connection. Now if you see, first transformer is delta star grounded, other is star grounded delta. So let us draw on this basis. This will be my reference bus. Now neutral of generator is grounded, so that neutral impedance will come as 3 Z generator. Then this will be J.2. Neutral impedance comes as 3 times the neutral impedance. Then transformer is star delta grounded. So series switch will be open. So we will short the shunt switch. Then we will place transformer impedance J0.0805. Then transmission line J.164. Then next transformer is star grounded delta. So on star grounded side we will operate series switch, and on delta side we will operate shunt switch. Series will be open circuited. Then out of the two motors, one has the neutral grounded, one has neutral ungrounded. So ungrounded impedance will come like this, 0.34. When the neutral is grounded, this will be 3Zm and J.68. Okay, because motor 2 has neutral ungrounded. So here Zn is infinity. Okay, so that is why we have shown open circuit. So this way, zero sequence circuit, you have to take care about the neutral grounding and the transformer connection. So let us summarize what we covered in this lecture. We first saw transformer sequence network, and there we saw different zero sequence network based on transformer connection. Then we saw transmission line. In transmission line we saw Z1 was equal to Zs minus Zm, Z2 was equal to Zs minus Zm, and Z0 was equal to Zs plus 2Zm. And then we saw how to draw the positive, negative and zero sequence networks independently of each other. In the next lecture, we will look at few problems based on the topics that we have covered so far in fault analysis, and then we will proceed on to how to analyze the faulty conditions in a power system. Hi guys, up to now what we have covered in fault analysis is, first we saw the per unit representation of the power system, then we saw the concept of symmetrical components, and then we saw how different sequence networks are designed for each and every component in a power system, that is generator, transformer and the transmission line. So in this lecture we will be solving a few problems that have come in GATE examination from these topics. So let us arrive at our first problem. The sequence voltages of an unbalanced three-phase system are given as V1 0.87 pu, V2 minus 0.57, V0 is minus 0.3 pu. We need to find the phase voltages. So here we need to calculate phase voltage from the symmetrical components. So the matrix that we will use will be, we will use our A matrix, that is VB, VC will be 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square. Then V0, V1, V2. That means VA will be V0 plus V1 plus V2, which will be minus 0.3 plus 0.87 minus 0.57, which is equal to 0 pu. So VA will be 0. VB will be V0 plus alpha square V1 plus alpha V2. Now this can be written as VB is equal to V0 is minus 0.3, V1 is 0.87, alpha square is 1 angle 240 plus V2 is 1 angle 120 into minus 0.57. So this will come out to be 1.325 angle minus 109.84 degree pu. Now VC will be V0 plus alpha V1 plus alpha square V2. Now as I told you, in the calc, the only thing that you have to do is you have to replace 120 and 240. So minus 0.3 plus 0.87 into 1 angle 120 plus 1 angle 240 into minus 0.57. So this will come out to be 1.325 angle plus 109.84 degree pu. Now these voltages we have arrived at in pu. It is asking the voltages on a voltage base of 11 kilovolt line to line. Now if the base voltage of line to line voltage is 11 kV, the base voltage of per phase will be, it will be 11 by root 3 kV. Now VA was 0 pu, so it will be 0 kV. VB will be 11 by root 3 into 1.325. So how much will this come out to be? 11 by root 3 into 1.325, that is 8.42 at an angle minus 109.84 degree kV. VC will be 11 by root 3 into 1.325, so it will have same magnitude, but angle will be 109.84 degree kV. So you must remember the matrices A and A inverse, because whenever the question comes from the symmetrical component, you can directly use those matrices. No need to remember the individual equations, just remember the matrix. And if you remember one matrix, you can form other matrix just by replacing A by alpha square and alpha square by alpha. In our next problem, it is saying an unbalanced system is having the sequence components like this. What is the power consumed by phase A on a base of 100 MVA? Now, simply I can write power consumed by phase A will be V1 I1 conjugate, V2 I2 conjugate, V0 I0 conjugate. Now V1 is 1.2, I1 conjugate will be 3 plus J4, that is 5 angle 53.13. Then V2 is minus 0.4 into 5 angle 53.13. Then V0 is minus 0.1, 5 angle 53.13. So this will be 0.7, that is, how much will this come out to be? 0.7 into 5, that is 3.5 angle 53.13 degree pu. Now base is given to be 100 MVA. So if we multiply it by base, it will be 350 angle 53.13 MVA. In real and imaginary terms, it will be 350 into 0.6, that is 210 megawatt, plus 350 into 0.8 will be 280 MVAR. Okay, so that will be your power consumed by A phase. Okay, just I have used the concept of power in terms of symmetrical components, and I haven't taken 3 because it is just asking the power consumed by A phase. If it were asking the power consumed by all 3 phases, then we will take the factor of 3 and we will take 3 V1 I1 conjugate, V2 I2 conjugate plus V0 I0 conjugate. In our next problem, it is saying a 3-phase transmission line supplies delta connected load Z. The conductor C of the line develops open circuit fault. That is why the current in C is 0. The currents are shown in the diagram. We need to find positive sequence component in A. We know IA1 will be 1 by 3 IA plus alpha IB plus alpha square IC. That is 1 by 3 tan angle 0 1 angle 120 multiplied by tan angle 180 plus 1 angle minus 120 into 0. So it will be 1 by 3 tan angle 0 plus tan angle 300. This will come out to be 5.78 angle minus 30 degree ampere. So that will be the positive sequence component of the current in phase A. Okay. So just you have to remember the matrix. This equation even I have written directly from the matrix. How? In matrix, if we write A inverse will be used, that will be 1 by 3 1 1 1 1 alpha alpha square 1 alpha square alpha. So this gives me the positive sequence, that is 1 then alpha square. In our next problem, it is saying, suppose we define a sequence transformation between ABC and PNO variables. ABC is the phase, PNO is positive negative 0 sequence, as follows. Alpha is e raised to power j pi by 3, k is a constant. Now we are given that Vp, Vn, V0 is some matrix into Ip, In, I0. We need to find the relation between Va, Vb, Vc and Ia, Ib, Ic. Now we know that Fa, or rather what is the need to write down, it is given here only. Fa, Fb, Fc is this matrix. So if you write Fa is k times Fp plus Fn plus F0, Fb is k times alpha square Fp plus alpha Fn plus F0, Fc is k times alpha Fp plus alpha square Fn plus F0. Now if you carefully observe, this is the same transformation that we did to arrive at the phase voltage or the phase quantities from the symmetrical components. Just it is that k is extra here. Now for inverse transformation, what to do is take this k on the left hand side, then write the inverse of this matrix. How? What we will write is F0. F0 will be 1 by 3. K will be taken in the denominator because K will become 1 by K here. Fa plus Fb plus Fc. Fp will be 1 by 3K Fa plus alpha square plus alpha Fb plus alpha square Fc, and Fn will be, that is negative sequence, 1 by 3K Fa plus alpha square Fb plus alpha Fc. How I have written this down? From the A inverse matrix, 1 1 1 1 alpha square 1 alpha square alpha. Okay, just a factor of k is additional because of the problem given to us. Now we have to write in the order Vp, Vn, V0, that is P then N then 0 sequence. So what will be the order? We will write it as Fp, Fn, F naught will be 1 by 3k, then 1 alpha alpha square, 1 alpha square alpha, 1 1 1, Fa, Fb, Fc. Now we have to arrive at Va, Vb, Vc from Vp, Vn, V0. Then we can use this transformation. We will replace Vp, Vn, V0 by Va, Vb and Vc. So this equation can be written as 1 by 3k, 1 alpha alpha square, 1 alpha square alpha, 1 1 1, Va, then Vb, Vc should be equal to, what is the matrix given to us in the problem? 0.500, 0.50, 0.50, 0 0 2. Ip, I and I0 can also be replaced like this, that is 1 by 3k, 1 alpha alpha square, 1 alpha square alpha, 1 1 1 into Ia, Ib, Ic. Now to derive Va, Vb, Vc, we will take inverse of this matrix. Now this matrix is itself inverse of this. This matrix here, suppose this is A, this is A inverse. So inverse of this will give me this matrix. So Va, Vb, Vc will be it will be 1, what is there, 1 1 1 alpha square alpha 1, 1 1 1 alpha square alpha 1 alpha alpha square 1 into k into 0.5 0 0 0 0.50 0 0 2 into 1 by 3k is also there. Then this matrix. Now k gets cancelled out, 1 by 3 will come outside. So what will be the matrix product that we have to calculate? 1 by 3, 1 1 1, alpha square alpha 1, alpha alpha square 1. Then 0.5 0 0 0 0.50 0 0 2. Then the next matrix is 1 alpha alpha square, 1 alpha square alpha, 1 1 1. Now we multiply the second and third matrix first of all. First row into first column will be 0.5. First row into second column will be 0.5 alpha, 0.5 alpha square. Then 0.5, then 0.5 alpha square, 0.5 alpha, then 2, 2, 2. Now multiply these two matrices. First row into first column will be 3. Then first row into second column will be 2 plus 0.5 alpha plus alpha square, that is minus 0.5. So 1.5. Then again it will be 1.5. Then 0.5 alpha square plus 0.5 alpha is minus 0.5 plus 2, that is 1.5. Then 0.5 alpha cube plus 0.5 alpha cube is 1 plus 2, 3. 0.5 alpha 4, that is 0.5 alpha, 0.5 alpha square is 0.5 alpha square plus 2, that is 1.5. Similarly, this row will be 1.5, 1.5, 3. If you divide it by 3, it will be 1.5, 0.5, 0, 0.5, 1.5, 0.5, 0.5, 1. That will be your Z matrix. Now this is a very complicated procedure and it is very long. So let us try to find it by some short method. Now if you observe first of all, if you transform both these matrices IP, IN, I naught and VP, VN, V naught, K will get cancelled out because K will come on both the sides. That means K has no role. Other than that, it is the simple matrix that we used in case of transformer, transmission line and generators. That is the basic matrix of symmetrical components. There is no trick involved. Just that K can be easily removed because it will come on left hand side as well as right hand side. Now if you see, these terms are similar to what we arrived at in transmission line. Positive sequence impedance was Zs minus Zm. Negative was Zs minus Zm. 0 was Zs plus 2Zm. Okay. And it is asking the relation between VA, VB, VC and IA, IB, IC. That was the original matrix, that is Zs, Zm, 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 Zs, Zm, 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 Zs. Okay. So it is asking the relation in the phase voltage and phase current given the relation between sequence components. We were going in the opposite direction. We knew the relation between the phase current and voltages. We were deriving the relation between sequence component. Now just by comparison, I know Zs minus Zm is 0.5 whereas Zs plus 2Zm is 2. Now if we add these two, Zm will become, or let us subtract these two, then 3Zm will become 1.5, Zm is 0.5 and from first equation Zs is 1. So this matrix will be this only, Zs is 1, Zm is 0.5. So this can be arrived directly if you remember the results for the transmission line. In our next problem, it is saying a three-phase transmission line is shown in figure. The voltage drop is given by this equation. This matrix was giving the voltage drop. Shunt capacitance of the line can be neglected. If the line has positive sequence impedance, that is Z1 is 15 ohm, Z0 is 48 ohm. Now we know Z1 is Zs minus Zm, which is 15. Zs plus 2Zm is 48. It is asking Zs and Zm. If we add these equations, subtract these equations, 3Zm will be 33. That is Zm will be 11. And Zs will be from first equation 26 because 26 minus 11 will be 15. So answer will be 26 ohm and 11 ohm. In our next problem, it is saying for the network shown in the figure, the zero sequence reactance in PU are indicated. What is the zero sequence driving point reactance of node 3? So first let us try to draw the zero sequence network. Here first of all generator is there. Its neutral is solidly grounded. So Zn is 0. Let me take a reference bus. Since neutral is grounded, so here we will show Zn is 0. Then generator zero sequence reactance is J.1. Then transformer is star delta grounded. Star means we will operate the shunt switch, keep the series open, then we will place 0.15 J. Then we will operate the series switch because star is grounded. Then transmission line will be J.05. Then again generator is there and its neutral is grounded. So we will have generator reactance like this. Neutral is grounded. So here Zn is 0. This is J.2. Here we have our bus number 3. It is asking the driving point impedance of bus 3. Now these two reactances are in series. So if you see bus number 3, this is series 0.2. This is again 0.2. So for bus 3, they both are connected in parallel. Hence I can say it is J.1. When two equal impedances are connected in parallel, equivalent is half of those. So it will be 0.1 pu. Okay. In our next problem, it is saying a three-phase alternator generating unbalanced voltages is connected to a unbalanced load through a three-phase transmission line. The neutral and star point of the load are grounded. This is the neutral of source. This is star point of load. Both are grounded. So this voltages can be written as minus plus, minus plus, minus plus. Because in star connection we will connect the negative of all the voltages together. The phase voltage are 10 angle 0, 10 angle minus 90, 10 angle 120. We need to find positive sequence component of load current. To find positive sequence component of load current, we need to find all the phase currents. So let us first try to calculate IA. IA will be 10 angle 0, that is EA, divided by this reactance, that is J2. So it will be 5 angle minus 90. Similarly IB, this is 10 angle minus 90 divided by J3, that is J1 plus J2, 3.33 angle minus 180. The next current is IC, which is EC 10 angle 120 divided by J4, that is J1 plus J3, 2.5 angle 30. Now to determine the positive sequence component IA1, it will be 1 by 3 IA plus alpha IB plus alpha square IC. That is 1 by 3 5 angle minus 90, 1 angle 120, then 3.33 angle minus 180 plus 1 angle 240 into 2.5 angle 30. So how much will this come out to be? It will be 3.51 angle minus 81 degree. Okay. So these sort of questions can come in the GATE examination based on the symmetrical components. And here the effort is very less. You just have to remember the matrices for the transformation. In our last problem of this lecture, it is saying three identical star connected resistors of 1 pu are connected to a unbalanced three-phase supply. The load neutral is isolated. Symmetrical component of line voltage are given. We need to find the components of phase to neutral sequence voltage. Okay. Now first of all let us talk about positive sequence. In positive sequence what happens? VAN, VBN, VCN. Now if you determine VAB, it will be VAN minus VBN. This will be VAB. So in positive sequence VAB leads VAN by 30 degree. And in per unit system there is no concept of phase or line voltage, hence the PU value remains the same. That is why VAN will be in magnitude same as the line voltage, but in angle it will be lagging the line voltage by 30 degree. Similarly, if we talk about negative sequence, it will be VAN, then VCN, then VBN. Now if we wish to calculate VAB, it will be VAN minus BN. It will lag the phase voltage by 30 degree, or we can say the phase voltage leads the line voltage by 30 degree. So VA2 will be having same magnitude, but angle will be leading the line voltage by 30 degree. Okay. So remember this concept, in per unit there is no concept of phase or line. All have the same magnitude in per unit. But phase shift in positive sequences, line voltage leads the phase voltage by 30 degree. In negative sequence, line voltage lags the phase voltage by 30 degree. In zero sequence, there is no component in line voltage, but zero sequence phase voltages can be present. Okay. So these sort of problems can be framed. Out of this, the most important are symmetrical components and the equivalent zero sequence reactance in case of a power system network. Okay. In the next lecture, we will start with the fault analysis and we will see how to analyze the faulty conditions existing in a power system. Hi guys, up to now in fault analysis what we have covered is, we have covered the tools that are required for fault analysis. First of all, we saw the per unit system, that is how to represent the entire power system in terms of PU. Then we saw the concept of symmetrical component, that is how to analyze an unbalanced system in terms of balanced components. Then we saw sequence network, that is how to design the power system equivalent circuit for different symmetrical components, that is positive sequence, negative sequence and zero sequence. So in this lecture we will be starting with our fault analysis, that is how to make use of the mathematical techniques that we have learned so far to analyze the abnormal conditions occurring in the power system. So fault analysis is basically analysis of abnormal conditions in power system. Okay, it is done prior to the occurrence of fault. It is not that the fault has occurred and then we are analyzing before the fault occurrence. Now fault analysis is divided into two parts. Short circuit fault, whenever there is a short circuit it is an abnormal condition, or there is a open conductor fault, whenever any conductor gets open circuited. Now in case of short circuit fault we have the following categories. First is your line to ground fault, that is one line is connected to ground. Out of three lines, one will be connected to ground. Other is line to line fault, that is two lines are short circuited together. Then next is LLG fault, that is two lines are short circuited as well as they are connected to ground. Then three phase short circuit, that is LLL fault, and last will be triple LG fault, that is all the three phases are short circuited as well as they are connected to ground. Now whenever the same condition is occurring in all the three phases, then their currents will have equal magnitude, voltages will also have equal magnitude, system will be balanced. So these two type of faults are balanced type of faults or symmetrical fault, because it is condition is symmetrical in three phases. These are called as unsymmetrical fault and they will make the system unbalanced. So we will require the method of symmetrical components for the analysis of unsymmetrical fault. In case of open conductor fault we have two categories, one conductor open or two conductor open. But in our gate scope we have only short circuit fault, so we will take a look at the analysis of short circuit faults. But the first thing that comes to mind is, why are we doing fault analysis? What is the purpose behind it? Why go through so much trouble to arrive at the fault current? The reason is, if we know the magnitude of fault current before the occurrence of fault, then I know how much current will be flowing in the system if a fault occurs. And if I know how much current will be flowing under faulty conditions, then I will devise a measure to open circuit the power system if such a current will flow. That is, if I know how worse the conditions can be in the power system at the time of fault, then we can design a effective protection system. Okay, now protection system has two parts. One is called as protective relays, other is your circuit breaker. Now the working of relay is, it has to sense the abnormal condition, then inform the circuit breaker that there is abnormal condition in the circuit, so circuit breaker can open circuit the power system. So relay must only sense. Now if I give you two currents, one is the minimum fault current, other is the maximum fault current, which current should the relay operate on? The answer is, it must always operate on minimum fault current, because if it can detect that 100 ampere is an abnormal condition, then definitely 200 ampere will also be a abnormal condition for the relay. But if you set 500 ampere as the abnormal condition, whereas the fault current is 100 ampere, it will think that 100 ampere is a normal current. There is no fault in the system. So fault will not be cleared. That is why relay must always operate on minimum fault current. If it can sense minimum fault current, it can sense a current higher than that. Now if we talk about circuit breaker, the function of circuit breaker is to open circuit the power system for the fault condition. That means it will actually open the current flowing in the circuit. Now suppose the current is high, then current density will be high. Okay. Then it will lead to high electric field intensity, which can cause ionization of the dielectric medium. This is called as arc. So whenever the circuit breaker will try to separate, an arc will be struck between the circuit breaker contacts, and till the arc is present, there will be current conduction between the two contacts via the ionized medium, because ionized medium will act as a conductor to conduct the current between the two plates. So if you have to actually open circuit, then you have to remove this arc. Now higher the current, dangerous is the arc. So that is why we need to know the maximum fault current, so that we know how much dangerous the arc can be, or what is the maximum arc intensity that I have to extinct. That is why circuit breaker are designed based on maximum fault current. Okay, got the reason? Because with the maximum fault current, arc will be the most severe, and we need to devise a method to extinct that arc, which we can only do if we have an estimate of maximum fault current. Next, let us look at the assumptions that we make for the short circuit fault analysis. First is, generator will be modeled as a constant voltage source behind subtransient reactance. I will explain the meaning of subtransient reactance later on, but this assumption just means that generator has a constant EMF under faulty condition. This EF remains constant. Next is, shunt element in transmission line is neglected. That is, the shunt admittance will be neglected. So what will be there? Only the series impedance, which is equal to R plus JX. The next assumption is, load current is taken as 0. That means the entire current will flow into the fault. No current will go through the load. Okay. Now that means we will remove any load. We will take fault under no load condition. That is, before the occurrence of fault, there was no load in the system. Why? Suppose if IA current is flowing in the power system, then VT will be EF minus IA XS, okay, or XT. That means VT will be low. But if we want to analyze the worst case scenario when the fault current is maximum, for that VT should be maximum. For that, this negative term should be 0. That is, IA must be 0 before the fault, or we can call it as pre-fault. Okay. If there is no load condition in the power system before the occurrence of fault, then VT will be maximum, due to which the current under faulty condition will also be maximum, as we want to analyze the worst case scenario or the most severe conditions in the fault. The next assumption that we make is, we will neglect all the loads in the power system except synchronous motor. Why? Suppose there is a synchronous motor. And we short circuit the terminals. Now it will act as a generator and it will supply current to the fault. Okay. Here the stored kinetic energy, because the rotor would have been rotating when the fault occurred, so it will have some kinetic energy stored in it. That stored energy will act as prime mover and it will be converted to electrical energy, which will be delivered to the fault. That means under faulty condition, the motor also acts as a generator and delivers current to the fault. So if we neglect synchronous motor, then what will happen? We are neglecting a part of the fault current. That is, we are underestimating the fault current, which is not a healthy practice. So we will consider synchronous motor as it will act as a generator. But we will neglect induction motor. Why we will neglect induction motor? See, induction motor does not have any field excitation. If it does not have any field excitation, that means it has to draw the entire reactive power from the supply to generate the flux. That is why induction motor always acts as at lagging power factor. So, when we will short circuit the supply, then what will happen is the reactive power that it was drawing from the supply, that is the magnetizing current, will go to 0. So there will be no excitation, hence induced EMF will be 0 under faulty conditions. Okay, so that is why we will neglect the induction motor under faulty condition, because it will not be able to supply the fault current. Okay, only synchronous motor can supply the fault current, not the induction machine. So we will neglect any passive loads and we will consider only the synchronous motor under faulty condition. Okay, so these are certain assumptions that we will maintain, and in case of generator we will assume that synchronous speed is constant, so that frequency is also constant under faulty condition. Next, let us see how we can compare the severity of different faults. Severity in the sense the magnitude of fault current. Now when we compare the severity, the line to ground fault is least severe. But as the number of phases involved in the fault increases, the severity will increase. So line to line fault will be more severe, LLG will be still more severe, but triple L and triple LG, this will be most severe. That means we will design the circuit breaker based on the three-phase short circuit fault. Okay, as I told you, circuit breaker is always designed on the basis of most severe type of fault, so it will be designed on the basis of symmetrical fault. Now, if you think when three phases are involved in the fault, okay, the probability that all the three phases are short circuited at the same time will be very rare, but one line can be grounded very easily. So the probability of occurrence of LG fault will be higher as compared to triple LG fault. So the chances of occurrence are 70%, 15%, 10%, and combinedly 5%. Okay, so three-phase short circuit fault are very rare, though they are the most severe type of fault. Okay, because all the three phases are short circuited simultaneously, that will be a very rare occurrence. Now one thing that must be striking in your mind is, how does a fault occur in a power system? What can be the possible cause of a fault? Now suppose there is a tree, there is a transmission line that is going from a tower. Now what happens if a tree branch falls on the transmission line? Then it will connect the line to the tower. So the current will flow from the line into the ground. So that will act as a LG fault where one line is grounded. So that is one of the most common causes, that when one of the tree branches falls on a transmission line, there is a line to ground fault occurring. Other than that, when we consider the tower, then transmission line are hanged by means of insulator. Now suppose by some means, that may be due to lightning over voltage, the transmission line voltage increases. Then what it can do is the air around the insulator may get ionized. If it gets ionized, there will be a arc formed between the conductor and the tower, due to which current will flow through the arc into the ground. So that will also cause line to ground fault. It is also called as arcing fault, because this fault has occurred due to the arc formation between the conductor and the ground. In case of bus bars, what we do is we have a very high dielectric strength, so there is very less chance of any arcing fault in case of a bus bar, and also we use hollow conductors in bus bars, so the electric field intensity is lesser, hence there is less chance of arcing fault. Now let us analyze the case in which we have a generator and a transmission line and we encounter a symmetrical three-phase fault. So this can be represented in circuit form like this, where Vt is the source voltage, R is the line resistance, L is the equivalent inductance. Okay, here Vt can be written as, it will be a AC voltage which will be Vm sin omega t plus alpha. Alpha is the initial phase of the voltage, and we are assuming that the fault occurs at t is equal to 0. Now, when we want to find the current flowing in the circuit, it will have two components. One will be the steady state current, other will be the transient current. Steady state current will be given by Vm by mod Z sin omega t plus alpha minus phi, and transient current will be some initial value, let us say I0, e raised power minus t by tau. Here mod Z is actually under root r square plus omega square L square. Phi will be tan inverse omega L by r, and tau is actually L by r. Now I know that we are assuming no load condition before the fault. So current at 0 will be 0. So at t is equal to 0, we can equate the current to be 0 because current cannot change instantaneously due to presence of inductance. So at t is equal to 0, I is 0. So 0 will be equal to Vm by mod Z sin alpha minus phi plus IT0 e raised power minus 0 by tau. So from here I can calculate IT0, it will be minus Vm by mod Z sin alpha minus phi, or we can say Vm by mod Z sin phi minus alpha. From here I can write IT Vm by mod Z sin omega t plus alpha minus phi plus Vm by mod Z sin phi minus alpha e raised power minus t by tau. Okay, this will be the total current flowing in the system. Now this will be your steady state component and this will be your transient component. Okay, there are two components in the current. So this will be the case for the fault occurrence at t is equal to 0. Now let us take another case when the fault occurs at some other time, let us say t is equal to t naught. Okay, fault is occurring at t is equal to t naught. Let me assume the voltage at, let us say just Vm sin omega t. Now current will have the same equation, Vm by mod Z sin omega t minus theta, let us say, plus I0 e raised power minus t by tau. Now we will say at t is equal to t naught, since no load condition would be acting, IT naught would be 0. So 0 will be Vm by mod Z sin omega t naught minus theta plus I0 e raised power minus t naught by tau. So if I calculate I0 here, it will be Vm by mod Z sin omega t naught minus theta into e raised power t naught by tau. So it will come out to be Vm by mod Z sin theta minus omega t naught e raised power t naught by tau. don't get confused by theta here. Theta is actually tan inverse omega L by R. Earlier I was representing it by phi, now I am referring it to as theta. So the total equation for current would become IT as Vm by mod Z sine omega t minus theta plus Vm by mod Z sine theta minus omega t naught e raised power minus t naught by tau. This term I have combined with the term e raised power minus t by tau. Now suppose a question comes, the condition for no transient. If there are no transient, that means the transient term should be 0. So theta minus omega t naught must be 0. T naught must be theta by omega. That is the condition in which there will be no transients in the transmission line. Only steady state current will flow. Now if we plot the transient and the steady state current, the transient current will be decaying exponentially. This will be sine theta minus alpha e raised power minus t by tau. This is my DC offset current. It is also called as DC offset current. Okay. Similarly, if we plot the AC current, which is also called as symmetrical fault current. Why symmetrical? Because it is symmetrical about the x-axis. So sine curve will be something like this. But we have sine omega t plus alpha minus theta. That is, I can also write as sine omega t minus theta minus alpha. That is right shift by theta minus alpha. So it will be like this. This angle will be theta minus alpha. So this is my symmetrical fault current Vm by mod Z sine omega t plus alpha minus theta. Now if we add these two currents, that is called as your, if we add these two currents, that will be called as asymmetrical fault current, because there will be DC component in the current. So it will not be symmetrical about x-axis. So how will it look like? This is the DC component. We will shift the signal by this much. Okay. So how will my current look like? It will look something like this. Okay, just I have shifted it upwards by an amount, DC offset current. So now if you see, it is not symmetrical about above and below the x-axis. Now the initial 1 or 2 cycles of the fault current is called as subtransient period. Then some more cycles is called as transient period, that is 3 to 5 cycle. And once the DC offset current is almost 0 and the steady state current settles down, it will be called as steady state period. Then the waveform will be symmetrical about x-axis, because transient would be decaying to 0. Okay, so that will be almost at 5 times the time constant, that is 5L by R. So if we define symmetrical RMS current, symmetrical current means the current which is symmetrical about x-axis. Definitely this will be just the AC current, because AC current will be symmetrical. So symmetrical RMS is how much? It will be Vm by root 2 mod Z, because Vm by mod Z is the maximum value, Vm by root 2 mod Z is the RMS value. Or we can directly say Vrms by mod Z. That is your symmetrical RMS current. What about asymmetrical? Then we know total current IT is Vm by mod Z sine omega t plus alpha minus theta plus Vm by mod z sine theta minus alpha e raised power minus t by tau. Now to find the RMS value of composite current, we will add the square of RMS value of each and every current. So I asymmetrical will be under root RMS value of this current will be Vm by root 2 mod z square. RMS value of DC current is same as the DC current itself. Vm by mod z sine theta minus alpha e raised power minus t by tau square. Vm by mod z can be taken as common under root half plus sine square theta minus alpha e raised power minus 2t by tau. This will be the asymmetrical RMS current. Okay. Now if we observe that the current decays when we go from subtransient towards the steady state region, so the current is maximum in the subtransient region and minimum in the steady state. So where should we open the circuit breaker, in the subtransient, transient or the steady state? See, if we open in the subtransient region, current will be highest. Then what will be happening? We won't be able to extend the arc that will be formed due to that high current. So we cannot open the circuit breaker in subtransient region because arc will be too dangerous. Then we cannot open in the steady state region also because steady state occurs after a long time. If fault current is allowed to persist for such a long duration, it can lead to system damage because high current flowing for a long duration will cause overheating of the system. That means we have to operate in the transient region. So circuit breakers are always opened in the transient region, not in the subtransient or steady state. So what happens is, if you are opening in transient region, still subtransient current will be flowing through the circuit breaker. It must be able to handle that much current, though it will not be opening at that current, but it should not get damaged at such a high current. So that means circuit breaker will have a rating that it can handle this much current for a short duration. That is called as maximum momentary current. So what will be the maximum momentary current? It will be the maximum fault current during subtransient region. Okay. Now current was Vm by mod z sine omega t plus alpha minus theta plus Vm by mod z sine theta minus alpha. Now the maxima will occur at omega t equal to pi. That is, t is equal to pi by omega. So what we will do is, we will neglect any decay of the transient current in that period because I want to do the worst case analysis. So I am assuming that the DC current or the transient current is at its maximum initial value. So we will take this term as 1. So it will be Vm by mod z sine of pi plus theta is minus sine theta, so it will become sine of theta minus alpha instead of alpha minus theta because it will become minus sine theta, plus Vm by mod z sine theta minus alpha. So it will become 2 Vm by mod z sine theta minus alpha. Now if we neglect the line resistance, the line impedance Z is actually R plus Jx. If R is taken as 0, Z will become equal to Jx. So angle theta will become 90. So I max will become 2 Vm by mod Z sine 90 minus alpha will be cos alpha. To further maximize this value, we will take alpha equal to 0. That is, I max will be equal to 2 Vm by mod Z. Okay. So it is twice the symmetrical current because symmetrical current has the amplitude Vm by mod Z. It is called as doubling effect. Okay. Now what does alpha represent? we were considering fault at t is equal to 0. So at t is equal to 0, what will be the voltage? It will be Vm sine alpha. So alpha indicates the initial voltage at the time of occurrence of fault. Taking alpha is equal to 0 reduces the voltage or the initial voltage to 0. Okay, that means at the time of fault, voltage was 0. If the fault occurs at the voltage 0, then the fault current is maximum, that is 2 Vm by mod Z. Similar concept we study in machines in terms of magnetizing inrush current. If transformer is switched on at voltage 0, then there is a doubling effect. Magnetizing current is most severe. Similarly here, if fault occurs at the voltage 0, then the fault current is most severe, that is twice the steady state current. Okay, it is similar to the concept of magnetizing inrush current. So let us summarize what we covered in this lecture. We first saw what is the scope of fault analysis. Then we saw what is the aim of fault analysis. What are the assumptions behind fault analysis? What are the causes of fault? Then we saw the transient, in which we derived current equation as Vm by mod Z sine omega t plus alpha minus theta plus Vm by mod Z sine theta minus alpha e raised power minus t by tau. Then we saw the symmetrical current. This is your symmetrical, and overall is called as asymmetrical. Then we saw maximum momentary current, which in the worst case was equal to 2 Vm by mod Z. But practically it will be less than this because we made a lot of idealities or lot of assumptions while calculating this value. Okay. So this is the general aspects of the fault analysis. In this, the transient analysis or transient on a transmission line is very important. Okay. So do remember this current expression for the gate examination. In the next lecture, we will see how does a synchronous machine reacts to a short circuit fault. What all physical phenomena occurs in case of a synchronous machine. That we will see in the next lecture. Hi guys, in the last lecture we started with the topic of fault analysis. There we first of all saw why we do the fault analysis, and we saw the aim of fault analysis was to design an effective protection system. There I told you that protective relays are designed on the basis of minimum fault current, and circuit breakers are always designed on the basis of maximum fault current. Then we saw various assumptions that we make in case of fault analysis, like generator is modeled as a EMF source in series with a subtransient reactance. We neglect any changes in frequency, those sort of assumptions. Then we saw causes of short circuit fault. Okay. Then we saw transients in the transmission line due to short circuit fault. There we derived current was equal to Vm by mod Z sine omega t plus alpha minus theta plus Vm by mod Z sine theta minus alpha e raised power minus RT by L. We derived this equation in which this was the steady state current and this was the transient current. So this was the transients in the transmission line due to a short circuit fault. Then we derived the maximum momentary current, which was the maximum current during the subtransient period. It came out to be 2 Vm by mod Z. So we called it as the doubling effect, as the maximum momentary current is twice the maximum value of steady state RMS current. We also saw the concept of symmetrical current and asymmetrical current. Symmetrical was the AC component because it was symmetrical about x-axis, Asymmetrical was the total current, that is DC offset plus AC, because it is not symmetrical about x-axis. In this lecture, we will study about the synchronous machine. How does it behave under the short circuit condition? So now suppose a synchronous machine is connected to a bus and there is a three-phase symmetrical short circuit fault. Three-phase symmetrical short circuit fault means all three phases are shorted. Since all the three phases are shorted, if we draw the equivalent circuit, we will represent something like this. This circuit is on per phase basis. Okay, this is my EF, J axis and R. Now what happens is, suppose we neglect R, then what will happen? This model will be something like this, EF by J axis. Now whatever the current will flow IF will be EF by J axis, that is EF by axis angle minus 90. So here I am assuming the angle of the EMF is 0. Instead of delta I have assumed 0, as I am assuming no load condition before the fault. If you are assuming no load condition, that means P is equal to 0, which is proportional to sine delta. So delta is also equal to 0. Okay. Now from here we can see that the fault current is 90 degree lagging. And we know in a synchronous machine, whenever the power factor is lagging, the armature reaction is demagnetizing. Now two effects will happen when the short circuit will occur. The thing is, whenever you will short circuit any machine, due to low impedance, the current will be very high. So IF is a very high current, because when we have short circuited, we have reduced the impedance and current becomes high. So IF is high. And the other thing is that IF is 90 degree lagging, due to which it has the effect of demagnetizing armature reaction. Now when the armature reaction is demagnetizing, it will tend to reduce the field flux. Now since IF suddenly increases, so it will try to reduce the field flux suddenly. But due to magnetic inertia, what is magnetic inertia? It states that flux cannot be changed instantaneously in a machine. So flux will not be able to change instantaneously. So some flux must be induced to oppose the effect of armature reaction, which will try to maintain the field flux constant. So flux will be induced in case of damper winding and also field winding. Earlier field winding was DC excited. Now AC current will be induced in field winding just so as to increase the field flux, so as to oppose the effect of armature reaction and maintain the flux constant. So now what will happen is, as the flux is induced, the initial period is called as subtransient period. There we will have leakage reactance, armature reaction. Since flux is induced in field winding and damper winding, so they will also have some flux. So this will be the model of the synchronous machine. The equivalent reactance is represented by Xd double dash. It is equal to XL plus 1 upon 1 by XA, 1 by XF, 1 by XdW. Okay, this will be the subtransient reactance of the synchronous generator. Here the flux is induced in field winding and damper winding, which tries to increase the field flux to oppose the demagnetizing armature reaction. Now usually what happens is, what is the use of damper winding in machine? As we have studied in case of machines, damper winding damps out the oscillation. Since it provides damping, it must have energy loss. So its resistance is high. Inductance will be low. So what we can say, L by R ratio is low. But in case of field winding, what is the purpose of field winding? to generate the flux for the machine operation. Now since it generates the flux, its inductance must be high and resistance must be low. Why the resistance should be low? So as to reduce the losses in the field winding. So if inductance is high, resistance is low, so L by R of field winding will be high. That means time constant of field winding is always greater than time constant of damper winding, due to which current will decay slowly in the field winding as compared to damper winding. Now, as I told you, flux cannot be changed instantaneously, so what will happen? Flux will gradually change, but it will change. How it will change gradually? Initially, to support the flux, currents are induced in damper and the field winding. Now these currents will start decaying. As they decay, the flux will go on reducing, but that will happen gradually. Now, the currents will decay with a time constant equal to tau. For a damper winding, that is a low time constant, and for field winding, it is high. Now, since damper winding time constant is low and field winding is high, currents will decay faster in damper winding as compared to field winding. When the current will decay, we will open circuit the damper winding reactance and the model will remain something like this. Here we have open circuited damper winding as IDW goes to 0. Whenever IDW goes to 0, such a period is called as transient period beginning. Transient period will begin when the current in damper winding is reduced to 0 and only armature reaction and field winding remain. The reactance is represented as XD dash. It will be XL plus 1 by XA plus 1 by XF. This will be the transient reactance of the synchronous machine under short circuit condition. Now eventually what will happen is the current will be decaying in field winding also. Which current? That is your AC current, not the DC current. DC current will be constant due to constant DC excitation. But AC current will go on reducing, and once it is reduced to 0, we enter the steady state period. So we will define XD, which is equal to XL plus XA. So the reactances of a synchronous machine under short circuit condition are time dependent. XD is a function of time. As the time passes by, it will change. So we have divided the time into 3 periods. One is your subtransient, second one is your transient, and last one is your steady state. Here we define the reactance as XD double dash, here XD dash, here XD. And if we compare the values, it will come out to be like this. So reactance will go on increasing as the current goes on reducing in case of a synchronous machine. Okay. So here we give the physical significance to the period subtransient, transient and steady state. Earlier I vaguely defined as 1 to 2 cycle is subtransient, 2 to 5 is transient, and after 5 cycles it will be steady state. But now we see what is the physical significance behind these 3 periods. Now suppose we plot the symmetrical short circuit current. Symmetrical short circuit current means AC current. We are not taking the DC offset. Now during subtransient period, what will happen is IF double dash will be EG by XD double dash. During transient period, IF dash will be EG by XD dash. During steady state, IF will be EG by XD. Now we know XD double dash is less than XD dash is less than XD, due to which current will have the opposite factors. IF double dash is greater than IF dash is greater than IF. So the current will go on reducing as the time passes by due to increase in reactance. Now in case of a fault, there are two currents. One is the steady state or the symmetrical current. Other is your transient or the DC offset current. Now DC offset current is exponentially decaying because of the resistance of the machine. We plotted DC offset current something like this in the last class. Okay. And the symmetrical AC current is decaying due to increasing reactance of the machine. Okay. So AC current will also decay as well as DC current will decay. AC will decay due to increase in reactance, DC will decay due to resistance of the machine. Now if we plot the reactance variation with time, what we are seeing is as the time passes by, current reduces and reactance increases like this. So this value we can call as xt double dash. After some time, we will enter the transient region. This is your subtransient and this will be your steady state. So this is how the reactance will vary in the machine. The reactance will change gradually, due to which the fault current will also decay gradually. But what we have approximated is, we have taken only 3 values of reactance. Instead of continuous variation, we are taking discrete variation. That is xt double dash, xd dash and xt. So we have just taken 3 steps in the reactances. We are not considering all the values. We are just considering 3 values. Okay. So it is a valid approximation when it comes to the short circuit modeling of the synchronous machine. Now let us discuss what are the effects whenever a short circuit fault will occur. Now usually what happens is, if we consider a lossless machine, then whatever is the mechanical input will be same as the electrical output. Why? Because later on what we will study is an equation called as swing equation, which is equal to Pm minus P. Now here d square theta by dt square is actually acceleration of the rotor of machine. Now under steady state what happens is, speed is constant, so acceleration must be 0, hence Pm must be equal to P. Now what happens as fault occurs? Suppose 3-phase short circuit fault will occur, then what will happen is, entire current will go into the fault, hence the electrical output of the machine is reduced to 0. Then what will happen? Pm minus Pe will be greater than 0, due to which acceleration will be positive and due to which speed will increase. So actually the rotor speed will be higher than the synchronous speed in case of a 3-phase short circuit fault. And if rotor speed increases, the frequency will also increase. But we made an assumption that the frequency remains constant under the short circuit fault condition. But here what we are seeing is, the physical effect of a fault is to increase the frequency of the system due to increase in the rotor speed. Okay, that is precisely the phenomena between hunting when the speed of the rotor changes due to sudden mechanical input on the shaft of motor. But this is the hunting phenomena, or this is the oscillations that we are studying in case of synchronous generator and not the motor. More details we will study about this in the stability chapter, so no need to worry about how this equation we arrived at and how we will be using it to determine the oscillations of the machine. So let us summarize what we covered in this lecture. We saw the short circuit model of the machine. Here we first saw the subtransient model, in which xd double dash was xl plus 1 upon 1 by xa plus 1 by xf plus 1 by xdw. This was the subtransient. Then xd dash, that is xl plus 1 upon 1 by xa plus 1 by xf. Then xd, that will be equal to xl plus 1 xl plus xa. And we saw that xd double dash is less than xd dash is less than xd. Okay. Then we studied about the effects of the short circuit fault, that is to increase the speed of the rotor or to increase the frequency of the system. Okay. In the next lecture we will see how to analyze different faults in the system, how to mathematically model them and derive whatever is the fault current or whatever is the current going into the fault in a system. That we will start from the next lecture onwards. Hi guys, in the last lecture we saw the short circuit model of a synchronous machine. Whenever a short circuit occurs at the terminals of synchronous machine, we defined three periods. One was your subtransient, the next period was transient, and the last period was steady state. In subtransient, we saw that since the flux cannot change instantaneously, currents were induced in the field winding and damper winding, due to which the equivalent reactance, that is subtransient reactance, was leakage plus 1 upon 1 by XA plus 1 by XF plus 1 by XTW. In case of transient, it was XL plus 1 by 1 upon XA plus 1 upon XF. In steady state, it was XL plus XA. These were the three periods that we defined in case of a short circuit on a synchronous machine. Also, we saw the effects of a short circuit fault, in which we saw the speed increases, due to which the frequency of the machine will also increase. In this lecture, we will discuss how to analyze the symmetrical short circuit faults. That means the faults which are identical for all the three phases, hence the system remains balanced. So in case of a symmetrical fault, what happens is the fault occurs symmetrically for all the three phases. So the system will remain balanced. And in case of a balanced system, there are no negative or the zero sequence circuits, or there are no negative or zero sequence components. Hence we will discuss only the positive sequence elements. So let us discuss here how to analyze these type of fault. First of all, first assumption that we will make is no load condition prior to the fault. No load condition means IA, IB and IC all were 0 before the fault, that is pre-fault. Okay. And VA, VB, VC were all balanced. Now what happens is that when the fault will occur, if we apply KCL at this node, then we see that there are three incoming currents, IA, IB and IC. There is no outgoing current, so the sum must be always 0. Okay. So they will always be balanced, that is IA will be IA angle 0, IB will be IB angle minus 120, IC will be IC angle 120. Now if we wish to calculate the symmetrical components of the current, then IA0, IA1, IA2. These will be equal to 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square. Then the currents will be IA angle 0, IB angle minus 120, 1 by 3, 1 alpha alpha square, 1 alpha square alpha. IC angle 120. Here we have to use A inverse matrix instead of A matrix to derive the sequence components. So now if we calculate IA0, it will be 1 by 3 IA bar, that is IA phasor plus IB phasor plus IC phasor. We just now saw the sum of these three is 0. IA1, it will be 1 by 3. So since all the currents are balanced, their magnitudes must be same. So I will call as I angle 0. Alpha is 1 angle 120 into I angle 1 minus 120. then alpha square is 1 angle minus 120 into I angle 120. Now these angles will get cancelled out, so it will be equal to I. Okay, and IA2 if we calculate, it will be 1 by 3 IA angle 0, or let us call it as I angle 0 since magnitude will be same, plus 1 angle minus 120 into I angle minus 120 plus 1 angle 120 into I angle 120. So if we simplify this, what we will get? IA2 will be 1 by 3 I angle 0 I angle minus 240 plus I angle 240. Now what are these angles? Minus 240 and 240. 0 is this one. Minus 240 is this. It will be minus 240 or plus 120. Then this is this is plus 240. So the sum of these three will also be 0. So here we saw IA0 is 0, IA1 was coming out to be I, IA2 comes out to be 0. Hence only the positive sequence current is present, which agrees with the initial hypothesis that we took. Now if we calculate the symmetrical component of voltages, if you see the network, the voltage of each phase was VA was equal to, let me show you, what is the voltage at this point? If we apply KVL, if we assume the voltage 0 here, it is IA into ZF. Similarly, VB will be IB into ZF, VC will be IC into ZF. IA ZF, VB is IB ZF, VC is IC ZF. Okay. Now if we wish to calculate the sequence components, we can write VA as IZF angle 0, VB as IZF angle minus 120, VC as IZF angle 120. Just I have kept the angles of I. ZF, let us assume that it is resistive. Okay, it is a valid hypothesis, otherwise you can assume the angle to be theta. Now if we wish to calculate symmetrical components of voltages, it will be 1 by 3 1 1 1 1 alpha alpha square 1 alpha square alpha. IZF I can take common, 1 angle 0, 1 angle minus 120, 1 angle 120. Now since the angles of the quantities are same as in case of previous matrix, I can directly write one thing. The results will be identical to what we arrived for the case of currents. VA0 will be 0. VA1 here will be IA into ZF. And VA2 will be 0. Okay. So how I am directly writing these is, because the voltage phasors have the identical phase as the current phasors that we saw earlier. Hence, we will arrive at the same result just with a different magnitude. So from here also we can see only the positive sequence voltage is existing. So this you can directly assume also, because we are having a balanced system, no negative or zero sequence components will be present. And here, since we have derived by symmetrical component methods also, only positive sequence component will exist. Now to draw the circuit on per phase basis. Why we are drawing on per phase basis? Because the system is balanced. You can analyze per phase and then you can manipulate the result to obtain the results for the other two phases. How to manipulate? You will just change the phase angle of the result and keep the magnitude same across all the three phases. Now from here, if we calculate the fault current from this circuit, okay, just we have drawn the positive sequence network, only positive sequence currents exist. So IF will be EF by Z1 equivalent plus ZF. Now this is your fault current. Suppose if ZF is given to be 0, in any problem if fault impedance is not given, you will assume it to be 0. So IF will be EF by Z1 equivalent. Now suppose we want to derive the power that is being delivered by the machine during the fault. So since we know IF is equal to EF by Z1 equivalent plus ZF, and in PU under no load condition, what will happen? IA will be 0. So EF will be equal to VT will be equal to 1 angle 0. So EF will be 1 PU. So what will be the IF in PU? It will be 1 upon mod Z1 plus ZF in PU. And what will be the power in PU? It will be equal to how much? EMF into current. Okay, because in PU power or S is equal to V into I. So it will be same as that of current. Now if we wish to calculate in actual values, what we will do is we will multiply the S by base value and we will multiply the base of 3 phase. So S will be equal to S base 3 phase by mod Z1 equivalent plus ZF in MVA. Now if you expand S base 3 phase, we know that Z base is equal to V base line to line square by S base. So from here I can substitute S base as S will be equal to V base square line to line by Z base into mod Z1 equivalent plus ZF in PU. Now when base impedance is multiplied by PU impedance, we will get the actual impedance. So it is V base square line to line by mod Z1 equivalent plus ZF. Okay, so this will be the short circuit MVA or the power delivered to the short circuit for a triple L fault or line to line to line fault. Okay, so this is your actual value MVA. In per unit value it is 1 upon Z1 equivalent plus ZF in PU. So that is how to derive the short circuit MVA. Next, in case of triple LG fault, this is the other type of symmetrical fault. Here what is happening is just that all the ZF has gone to 0. So what will be the fault current? It will be EF by mod Z1 equivalent. What will be IF in PU? It will be 1 upon mod Z1 equivalent in PU. So what will be S? That will be 1 into 1 upon mod Z1 equivalent. So that is 1 by mod Z1 equivalent in PU. So what will be the S in actual value? This will be S base 3 phase upon mod Z1 equivalent PU. So this is the case for a triple LG fault. Just it is a special case of triple L fault, just with an assumption that fault impedance is 0, because here all the three lines are grounded. If they were interconnected with each other, you will take a impedance ZF. Otherwise, what you can do is, even if you want to assume ZF, you will assume here, like all the three lines will be connected to ZF, then ground. So this will be ZF if you want to assume. Otherwise, you can take ZF is equal to 0 for the case of triple LG fault. So these are the two types of symmetrical short circuit fault in which all the three phases experience the same short circuit condition, or hence the three phases will be identical. Hence the system will be balanced. Now, as I told you, three-phase short circuit fault is the rarest as well as it is the most severe type of fault. Hence, the circuit breaker rating will be decided on the basis of three-phase short circuit fault. Now, what all ratings can we derive from the three-phase short circuit fault for the selection of circuit breaker? So, first the procedure is to calculate symmetrical short circuit current. What is a symmetrical short circuit current? That is the AC component of the short circuit current that we were just calculating by using EF and mod Z. That will be your symmetrical short circuit current. Now, we define two ratings of a circuit breaker based on this symmetrical short circuit current. One is rated maximum momentary current and other is symmetrical breaking current. Symmetrical breaking or symmetrical interrupting. So here, once we have I symmetrical, what we do is we will multiply it by 1.6. That will be the rated momentary current of the circuit breaker. Okay, that means the momentary current, that is the current that exists for a short duration, can exist only up to this much value. The short duration current should not exceed this value. That is your rated momentary current. Now, why we have multiplied it by a factor of 1.6? Because the symmetrical short circuit current contains only the AC component. It does not consider any DC current. Now, instead of simplifying the DC current using exponentials and all, what we are doing is we are taking an estimate of the DC current, that is 0.6 times the AC current. Hence, the total current will become 1.6 times the symmetrical short circuit current. So, instead of calculating the transient current, we are multiplying the whole current by an empirical factor to account for the DC offset current. Similarly, in case of symmetrical interrupting current or symmetrical breaking current, the first thing to be remembered is we will use XD double dash for generator and XD dash for motor. That is subtransient reactance of a generator and transient reactance of a motor, because in case of motor, since the supply is short circuited, so it does not have any supply, so the motor will decelerate and it will enter the transient region faster as compared to a generator. So we will consider transient reactance of a motor and subtransient for a generator. Based on this, we will first calculate I symmetrical. Then we will multiply it by an empirical factor to account for the DC offset current. Now, whenever you are opening the circuit breaker, the current which is the circuit breaker is encountering is called as symmetrical breaking current. Okay. So, the later you open the circuit breaker, the lesser the current it has to open circuit. The earlier you open it, higher will be the current. Why? Because as the time passes, DC offset current decays down to 0. In steady state, the DC offset current is 0. In subtransient, the DC offset current is highest. So, the factor that you have to multiply with the symmetrical current depends on the value of speed of the circuit breaker. That is, when you are opening the circuit breaker, either you are opening it early, then you will multiply it by a high factor. If you are opening it late, then you will multiply it by a low factor. So let us see what factor we have to multiply. Okay, and as I told you, mostly you will open in the transient region and not in the subtransient or the steady state. Now if you take 8 cycles speed, okay, speed is greater than 8 cycle or time is greater than 8 cycle. So it is taking a very large time. In 8 cycles, the DC offset current will almost have decayed to 0. If it has decayed to 0, then the only current that remains is symmetrical short circuit current. So we have to multiply it by a factor of 1. No need to multiply it by any other factor because the DC offset current is almost 0. Now if we are taking a 5 cycle circuit breaker, that is it opens in 5 cycles, then we will multiply it by 1.1. Then 3 cycle, we will multiply it by a factor of 1.2. Then 2 cycle, 1.4. We do not go beyond 2 cycles. Why? Because beyond 2 cycle we will enter the subtransient region, and we open the circuit breaker always in a transient region. We never open the circuit breaker in subtransient because the current is very high, due to which the arc formed will be very dangerous and it will be hard to extinct. So we will open only in the transient region. Now let us look at a problem to illustrate how to use these symmetrical short circuit fault concepts to solve a problem. It is said that a 25 MVA 11 kV generator has XG double dash 20%. Okay. Now it is connected through a transformer, a line and a transformer to a bus that supplies 3 identical motor. Now each motor has XG double dash 25% and XD dash as 30% on a base of 5 MVA 6.6 kV. Okay, so motor has a base 5 MVA 6.6 kV. Generator has a base 25 MVA 11 kV. The rating of step-up transformer. Now the step-up transformer will be connected nearer to the generator because before transmission we will step up the voltage. 25 MVA 11 by 66 kV and leakage reactance is 10%. Okay, step up is 0.1. Then step down transformer is 25 MVA 66 by 6.6 kV with a reactance of 10%. Step down is also 10%. The bus voltage at the motor is 6.6 kV when a three-phase fault occurs at F. The reactance of transmission line is 15% on a base of 25 MVA 66 kV. Assuming no load, we need to assume system base as 25 MVA. Now step 1 in fault analysis is to draw the equivalent circuit or the per unit reactance diagram. So this is the circuit that is given to me, or this is the single line diagram. We have to first convert it to a per unit reactance diagram. So what were the rules? We will first divide the circuit based on transformers. This is zone 1, zone 2, zone 3. Now he has said that assume the base as 25 MVA. Now we do not know the voltage base, neither it has given. But if you see the rated values, for generator rated voltage is 11 kV. For this it is 11 by 66. Hence here the voltage will be 66. For this it is 66 by 11, 6.6. So here the voltage will be 6.6, which is actually the rated voltage of the motor. So if you guys are assuming any base in any problem, try to assume a base which requires minimum computation. That is, you have to change the minimum number of values and mostly the values will remain same. Okay. So for the generator, now if we calculate the subtransient reactance, given is 0.2. The voltage at which it is given is 11. New base that we have assumed is 11. The base MVA that is we have assumed is 25, given is 25. So it will remain as it is. For transformer T1, given is 0.1. The voltage at primary which is given is 11. What we have assumed is also 11. The base that we have assumed is 25 MVA, given is 25, J.1, which will be same as that of T2. Because T2 also the rated voltage is 66 by 6.6 and we have assumed 66 here, 6.6 here. So voltage is also same as rated and MVA is also same as rated. For transmission line, it is given as 0.15. The base is given 66 kV and we have assumed the base for transmission line as 66 kV. The base given for the transmission line is 25 MVA. We have also assumed 25, so it will be J.15. Now for the case of motor, the voltage that is given at the motor terminals is 6.6 kV, and we have also assumed 6.6. So given is J1.25, sorry, J.25, 25%. The voltage that is given is 6.6. We have assumed 6.6. The base that we have assumed is 25, given is 5. So it will be J1.25, which is equal to XT double dash. Similarly, the transient reactance will be J.3. 6.6 is given, assumed is also 6.6. 25 is assumed, 5 is given. So it will be J1.5. That will be XT dash. Now since we have all the reactances and impedances on the same base, we are ready to draw the per unit reactance diagram. So how will it look like? It will look something like this. This is your generator reactance. This is step up transformer, transmission line, step down transformer. Then the three motors which with impedances J1.25. Now the first question that we have to solve is we have to find the subtransient fault current. That is the current going into the fault during the subtransient period. Since we are talking about subtransient, I have used the subtransient reactance of the motor. Now since fault is occurring at F, we have grounded the point F. Now see how the current will flow. Current will go like this from the generator, from this motor like this, and like this. All the machines will be delivering the current into the fault. And as I told you, under faulty condition, motor will act as a generator and it will deliver current to the fault. Now fault current will have four components. First coming from a generator, 1 divided by how much is the reactance? 0.1, 0.2, 0.3, 0.45, 0.55. For motor it is J1.25, and all the three motors will have same current, that is into 3. So how much will this current come out to be? The short circuit current, it will be minus J 4.22 pu. Now the fault is occurring at the terminals of motor here. So it is lying in region 3. To calculate actual value, we will have to calculate the base current in region 3, which is 25 MVA by root 3 into 6.6. So this base current will come out to be 2187 ampere. So what will be the fault current? That is 4.22 into 2187, that is equal to 9229 ampere. That will be your fault current or the subtransient current going into the fault. Okay. So first rule to remember is whenever the fault will occur, all the machine, whether it is a synchronous motor or a synchronous generator, they will deliver the current into the fault. In our next problem, it is asking subtransient breaker current. So first we have to locate the circuit breaker. Circuit breaker B is this and fault is coming here. Okay. So fault is coming between the breaker and the machine. So if breaker is here, fault is coming on the right side of the breaker. Now this current will go directly into the fault. This current will go like this. This will go like this. This will go like this. So three currents will have to pass through the circuit breaker to go into the fault. But the motor at which the fault is occurring, the current will directly go into the fault, because for that motor, breaker lies after the fault. Okay. What I am saying is, I will show you in this figure. See, if the current from the generator goes into the fault, it has to go through the breaker. It will go like this. For this machine, if it goes into the fault, it has to go like this through the breaker. For this machine, if it goes, it has to go like this through the breaker. But for this machine, it can directly go into the fault without going through the breaker. So only 3 currents will pass through the circuit breaker. One will go directly into the fault. So whenever we are calculating subtransient breaker current, we will take generator current, that is 1 by J 0.55. We will take the current of 2 motors and not the all 3 motors. So how much will this come out to be? Minus 3.42. So base current will remain same because breaker B also lies in the region number 3, 2187 ampere. So I will be 2187 into 3.42. So it will be 7479.5 ampere. That will be your subtransient breaker current, or the current going into the breaker in the subtransient region. Next we need to calculate momentary breaker current. As I told you, rated momentary current can be calculated as 1.6 times symmetrical current. This symmetrical current will be the current passing through the breaker, which is equal to 7479.5. Hence it will be 11967 ampere. This much current will be the rated momentary current of the breaker. That is, it can handle this much current for a short duration of time, not for a long duration. Calculate is the symmetrical breaking current. But the first rule that I told you about the symmetrical breaking current, instead of XD double dash, we have to use XD dash. Now, here we have used J 1.25. So first we will have to replace each with 1.5. Because as we calculated, XD dash is 1.5. Now, the current going into the breaker was the generator current plus the current of the 2 motors. Okay, because one motor current goes directly into the fault before passing the breaker. So it will be J 2 into 1 by J 1.5. So how much will this come out to be? Minus J 3.1515 pu. Okay, this will be the breaker B current. Now, to find the breaking current, we have to take the speed of the circuit breaker into the account. So let me assume 5 cycle circuit breaker. So I breaking will be 1.1 into 3.1515 pu, and the actual value will be, it shall be multiplied by the base current, which is 2187. So how much will this come out to be? 7581 ampere. Okay, so that is how you calculate the symmetrical breaking current of a circuit breaker. First, replace the subtransient reactance of motor by transient reactance, calculate the symmetrical current, and then multiply it by a factor corresponding to the speed of operation of circuit breaker. So let us summarize what we learned in this lecture. We first saw the triple L type of fault. There we saw only positive sequence component can exist and there is no negative or zero sequence component. There we saw the fault current in PU was 1 upon mod Z1 equivalent, that is the equivalent positive sequence impedance, plus mod ZF into PU. This should be in PU. And we saw the short circuit MVA in PU. It was same as the fault current, Z1 equivalent plus ZF PU, which was also equal to base MVA in 3 phase divided by mod Z1 equivalent plus ZF in PU. This was also equal to V line to line base square by mod Z1 equivalent plus ZF in ohm. Okay. Then we saw the momentary current of a circuit breaker, which is 1.6 times I symmetrical, and we saw the breaking current, that was K into I symmetrical, where K depends on speed of circuit breaker. It is 1.1 for 5 cycle circuit breaker, 1.2 for 3 cycle, and 1.4 for 2 cycle circuit breaker. Okay, so this is what we covered in this lecture. Rest of the symmetrical fault analysis we will see in the next lecture. Hi guys, up to now whatever we have covered in fault analysis was centered around the symmetrical fault analysis. That is, we were considering the faults which were symmetrical in all the three phases and hence the system remained balanced. So in this lecture what we will do is, we will consider different cases of symmetrical fault analysis based on the problems that have come in the GATE examination, so that you get a fair idea of what kind of problems can be asked and how to tackle those sort of problems. So let us get started with the first problem. It is saying a three-phase generator rated at 100 MVA 11 kV is connected through circuit breaker to a transformer. Now first thing, whenever you are given a fault analysis problem and you are being given the configuration of the network, then if you are not given the figure, try to draw the figure alongside. So it is saying a generator is there which is connected through a circuit breaker to a transformer. Okay, the generator has subtransient reactance 26% and synchronous reactance 130%. The generator is operating at no load and rated voltage. What does the rated voltage signifies here? That the voltage is 1 angle 0 degree PU. This is your VT, and due to no load, what I understand is IA is 0, so EF will be equal to VT, hence which will be equal to 1 angle 0. Okay. When a three-phase short circuit fault occurs between the breakers and the transformers, so here we are getting a three-phase short circuit fault. We need to find the initial symmetrical RMS current in the breaker. Initial means subtransient. Symmetrical RMS current means only the AC component. Okay. So, initial symmetrical RMS current will be EF by XD double dash, because the circuit is short circuited here. So the EMF of this generator is EF and the impedance is 0.26. So it will be 1 by J 0.26. So how much will this come out to be? 1 divided by 0.26, that is 3.846 angle minus 90 degree PU. Now to calculate the actual value, we need the value of base current. The value of base current can be calculated from the S rating or the MVA rating and the voltage rating. So how will you calculate? You have to calculate the base current first. That is 110 MVA by root 3 into 11 kV. So this will come out to be 5.77 kiloampere. Now what will be the actual value of current? It will be the base current multiplied by your per unit current. So per unit current is 3.846. So fault current is 3.846 into 5.77. So it will come out to be 22.2 kilo amps. Okay. So remember, whenever we are talking in per unit, the per unit current will remain same throughout the system, because in PU the entire network is connected in series and there is no transformation ratio. But if you are talking about actual current, then first see in which section we are trying to determine the current and use the base current for that particular section. Because whenever there will be transformers, then you have to use the base current of a particular section to determine the overall current. Now let us move on to the next problem. It is saying 4 identical alternators, each rated 20 MVA 11 kV, having subtransient reactance 16%, are operating in parallel. So how the system looks like? These are 4 alternators. This is their reactances, and all are operating in parallel. It is asking the short circuit level at the bus bars. Now we will assume no load condition. So in general we will assume 1 angle 0 as the EMF. The reactance of each generator is 0.16 pu. Now when you wish to calculate the current, now as I told you, every machine will try to deliver the current into the fault. So how will the current flow? Like this, from here and here. So since this is short circuited, this is grounded. So the current will be 4 times the individual current. Individual current is J.16. So it will be J.04. So 100 by 4 will be 25 angle minus 90 degree pu. Now S will be VI conjugate. So it will be 25 into 1, that is 25 pu. So in actual value it will be 25 pu into base. Base is 20 MVA. So it will be 500 MVA. This is the short circuit level at the bus bars. So remember, in case of a 3-phase short circuit fault, the per unit value of fault current is same as the per unit value of short circuit MVA, because the voltage at no load is equal to 1 angle 0, which is equal to the rated voltage. So we can directly say per unit MVA is same as your per unit fault current. In our next problem, it is saying in a power system with negligible resistance, the fault current to a point is 8 pu. So fault current is given as 8 pu. The series reactance to be included at fault point to limit short circuit current to 5 pu. Whenever we are talking about power system, so one thing that you must remember is we will replace the power system by a Thevenin equivalent. That is V Thevenin in series with X Thevenin. Now it is connected to a bus bar. So what happens is that fault MVA IF is 8 pu. So IF is equal to actually 1 by X Thevenin, which is equal to 8 pu. So it implies X Thevenin is equal to 1 by 8, which is equal to 0.125 pu. Now we are considering a series reactance. So the system will look something like this: X Thevenin, X series. So the fault current must be 5 pu, which will be equal to 1 upon X Thevenin plus X series. So here X Thevenin plus X series will come out to be 0.2 pu, which implies X series will be 0.075 pu. Okay, this much reactance must be included in series to limit the fault current to 5 per unit. Now, there is a catch here. The assumption that I have made is no load condition. How I am saying that I made this assumption? Because I took the voltage as 1 angle 0. So if the fault occurs under no load condition, then you can take the voltage directly as 1 angle 0. because no current will be flowing and there will be no voltage drop, and hence the voltage will be same as the rated voltage. In our next problem, it is saying the below diagram shows the layout of a power system. I have shown the diagram in the next slide. Having two generators A and B connected to 11 kV bus. So these are the two generators A and B connected to the 11 kV bus, which are also fed through two transformers C and D from a 132 volt grid. This is the 132 volt grid. This is the transformer C and transformer D. Now, the reactance of A, B, C, D and R are in PU a common MVA kV base. All the generated voltage in AB and grid are 1 PU and assumed as in phase at the time of fault. So, VA is equal to VB is equal to V grid. It is saying they are 1 PU and all are in the same phase. Since all are in the same phase, it implies that all the angles will be same. I am assuming the angle as 0 degree. The steady state symmetrical three-phase fault current on the feeder. Okay. So here the fault is shown. We have to first draw the equivalent circuit. So how we will draw? 1 angle 0, J.2, then here 0.1. We are saying that grid source has a negligible reactance, so we will simply replace it as 1 angle 0. This will be J.2. This will be 1 angle 0, J.2. Now it is very difficult to simplify this network directly. So what I will do is, I will divide this middle source into two parts. One with this J.2, other with this J.2. So how it will look like? 1 angle 0, 1 angle 0, this will again be 1 angle 0, this will again be 1 angle 0. So I have just divided a voltage source connected in parallel with two devices as individual two voltage sources. J.1, 0.2, 0.2, 0.2, 0.2. Now since both the EMFs are same, we can replace it by a single EMF source having the voltage 1 angle 0, and the reactance will be in parallel combination of J.2 and J.2, that is J.1. One angle 0, this is J.1, then 1 angle 0, this is J.1, and here we have a fault. Now this generator will supply the current something like this, and this will supply directly. So whenever we are calculating the fault current, we will compute the sum of the two generator currents. The first generator current will be 1 upon J.1, that is 10 angle minus 90. Other will be 1 upon J.2, that is 5 angle minus 90. So total overall fault current will be sum of the two, that is 15 angle minus 90 degree PU. Okay, that will be the fault current in the system. So the entire problem in the fault analysis, that too for a symmetrical fault analysis, revolves around simplifying the equivalent circuit of the system. If you are able to combine the reactances and the voltage sources, then the problem will reduce to a very simple problem of just the basic network solving. In our next problem, it is saying 4 identical 100 MVA 33 kV generators are operating in parallel as shown in two bus bar section interconnected through a current limiting reactor XPU. Now what is a current limiting reactor? Basically a current limiting reactor is connected between the two buses to limit the short circuit fault current, because by connecting this reactor we are effectively increasing the reactance and hence decreasing the fault current. Each generator has a reactance 0.2 pu. The value of reactor X to limit the symmetrical short circuit current through the circuit to 1500 MVA. So we are given the short circuit MVA as 1500 MVA, and if we assume the base as 100 MVA, so it is how much? 1500 by 100, that is 15 pu. Now we know whatever is the short circuit MVA in pu, the same is the fault current in pu. Okay. So now we have to compute the fault current and equate it to 15 to derive the value of X. So first let us draw the equivalent circuit. So this is one generator. This is second generator. This is your current limiting reactor. This is third generator and this is fourth generator. J.2, J.2, J.1. So this is X, not J.1. We will write it as Jx, J.2 and J.2. All the EMFs will be taken as 1 angle 0. Now you can combine these two sources in parallel and these two in parallel. The fault is occurring here. So how will this be reduced? This will be 1 angle 0 in series with parallel combination of the two, that is J.1 in between a reactor X and then the other generator, that is 1 angle 0 in series with J.1. Now fault is occurring here, so one current will go directly, other will flow like this. So 15 will be equal to 1 by 0.1 plus 1 by 0.1 plus X. 15 minus 1 by 0.1 will be 10. So it implies X will come out to be 0.1 pu. That will be the current limiting reactor X to be installed to limit the short circuit fault current to 15 pu. Okay. So that is how we design the rating and the value of the current limiting reactor for the case of power system protection, or based on the fault analysis. In our next problem, it is saying a 50 Hz alternator is rated as 500 MVA 20 kV with XD is equal to 1 pu and X double dash D is 0.2 pu. Now it supplies a purely resistive load of 400 megawatt at 20 kV. Now see, before the fault we are given a load. So this is the case of a loaded system. It is not the case of a no load system. Now this load is directly connected across the generator terminals. So what is happening is, this is my generator J1 EF. Here we have a purely resistive load like this, 400 megawatt. So I can calculate IR or IL, 400 into 10 raised power 6 by, or let us rather solve this in pu. So I will assume base as 500 MVA and 20 kV. So what is 400 megawatt in pu? That is 400 by 500, 0.8 pu. Now since the voltage is at the rated, that is 20 kV, so voltage is equal to 20 by 20, that is equal to 1 pu. Now since voltage is equal to 1 pu, power is 0.8 pu. Power is actually VI cos phi in per unit. 0.8 is equal to 1 into I into power factor is given as unity. So current will be 0.8 pu. Now, as I told you, in case of a symmetrical fault analysis, the assumption that we made was generator was modeled as a constant voltage source behind subtransient reactance. So the EMF of generator must remain constant under even the faulty condition. So let us calculate EMF. EMF will be Vt plus J IAXT. Vt is 1 angle 0 plus J into XD is 1 into I is 0.8. This will be 1 plus J 0.8 pu. Now what happens when the fault occurs? The entire current will go into the fault and we will enter the subtransient region. So how will my system look like? Since we enter subtransient region, the reactance become 0.2. This is the short circuit. So IF will be 1 plus J 0.8 divided by J 0.2. So this will be minus 5J plus 4, which comes out to be 6.4 pu. Okay. So that is how you can calculate the fault current for the case of a loaded synchronous machine. Okay, that is whenever the machine is supplying a load, first calculate the EMF and then use that EMF to find the fault current. The other method to deal with a loaded synchronous machine is to first obtain a steady state solution, that is the solution of the system before the occurrence of fault. In steady state solution, what you will compute is all the currents and voltages at any point of interest. Then what to do is, in the next step, you will have to replace all the reactances by their subtransient values. Okay, and we have to make all the EMF sources as zeros, that is short circuiting. Now what we will get is here a passive Thevenin network. Why passive? Because there is no energy source, so there is no active network. Now we will excite this network by negative of pre-fault voltage in series with fault impedance ZF. Okay, I will show you how it is done. Then we will compute post-fault current as pre-fault current plus fault current. Fault current will be calculated from the step number 3. So this is how we deal with the case of a loaded system. So this is one of the other methods that is based on the Thevenin equivalent. But I would recommend you the first method, in which we found out the EMF, as that is the most accurate method. If you are able to apply such a method, then it is the best way out possible. But in many books you will see that they have done the problems based on this Thevenin. That is why I am telling you this, otherwise it is not much relevant to the GATE exam. You can follow the EMF method, that will give you exact results. So let us see this method with the help of a problem. It is saying a synchronous generator and motor each rated 25 MVA, 11 kV, 15% subtransient reactance are connected through a transformer and a line as shown. The transformer is rated as 25 MVA, 11 by 66 and 66 by 11. So now first we will divide the power system into section based on transformer. Now if you see here, all the devices have the power rating of 25 MVA. So why not assume it as the base? Then we will have to change a lot less values. Now generator has a voltage of 11 kV. So let us say 11 kV is the base. This transformer is 11 by 66. So the secondary voltage will become 66. This is 66 by 11. So secondary will become 11 kV. So now we have got the base of each and every system. Now generator base remains same, 25 MVA, 11 kV. So reactance will also remain same, J.15. Transformer base is 11 kV, 25 MVA. So reactance will remain same, J.1. Line has a base of 25 MVA, 66 kV. which is same as earlier. So it will be J.1. Similarly, transformer T2 has also the same base J.2. Now motor is drawing 15 megawatt at 0.8 power factor leading. So this is the load on the system before the occurrence of fault. Hence it is the case of a loaded system. Terminal voltage is 10.6. So let me calculate the PU values. 15 by 25, that is equal to 0.6 PU. And terminal voltage is 10.6, which will be divided by 11 because it is talking about section number 3. So it will come out to be point how much? 9636. Okay, this will be the terminal voltage. To calculate the current before the occurrence of fault, what we will do, we will divide the power by V cos phi. That is I pre-fault will be 0.9636 divided by, power, that is 0.6 divided by 0.9636 into power factor. Power factor is 0.8 leading. So this current will come out to be 0.7783. Since it is leading, angle will be 36.9 degree PU. Because voltage angle we are assuming as 0. So current angle will be positive. So it will be greater than voltage. It leads the voltage. Now we have analyzed the step number 1, that is we have obtained the steady state solution before the occurrence of fault. Now there are two ways forward from here. One is to calculate the EMF of generator as well as the motor to determine the fault current. Other is the Thevenin method. Now if we draw the equivalent circuit, how will it look like? First we will have the generator. Generator will have a subtransient reactance 0.15. This will be Eg. Then there will be transformer with its leakage reactance J.1. Then there will be transmission line J.1. Then next transformer J.1. Then next motor J.15. Then this will be E motor. Now exactly what is happening is the fault is coming here. So here I know what is the voltage as well as the current before the occurrence of fault. Current will be flowing like this. Now, so there are other two ways. We know the voltage here is 0.9636 angle 0. So what you can do is, you can, based on this voltage and current that we have found out in the previous step, calculate Eg and Em and then short circuit this point to determine the fault current. That is the exact analysis. But other way around, what you can do is, in the next step it had asked us to remove all the voltage source and we will get a passive Thevenin network. So what you will do is, you will remove this voltage source, short circuit this. So the network that will remain is these four are in series. This will be 0.45. And this will be in parallel J.15. This will be the network that will remain. This is my fault point. Now we have to excite it by the negative of pre-fault voltage. That is how negative positive. So I am connecting it to the negative terminal in series with fault impedance, which is not given in this question. So we will take it as 0. So this voltage is 0.9636 angle 0. Now the current flowing through this 0.45 will be actually generator current. So generator current during the fault will be 0.9636 by J.45. How much will this come out to be? If you divide 0.9636 by J.45, it will come out to be minus J 2.141 pu. Similarly, motor current during the fault Now when you will ground this, the current will flow out of the motor. That is, current will start delivering the current. Sorry, motor will start delivering the current 0.9636 by J.15. How much will this come out to be? Minus J 6.423 pu. Now earlier motor was absorbing the current, now it is delivering the current. So the direction of current is reversed. So the total current in motor, or we can say I motor post fault, will be pre-fault current plus your during the fault current. Pre-fault current was 7.7783 angle 36.9. Now we will have to subtract this current because this current is going out of the motor. Earlier current was into the motor. So it will be 6.423 J. So this comes out to be 6.918 angle 84.83 degree pu. Similarly, if we talk about generator, in generator earlier also it was delivering the current, now also it is delivering the current. So I generator post fault will be 0.7786 angle 36.9 plus minus 2.141 J. We will have to add both the currents. So it will be 1.7856 angle minus 69.6 degree pu. Okay. Now if you see here, the voltage is actually angle 0, but the motor current is coming angle 84.83. That is, the motor current is leading the voltage. Now how come, as I told you, the fault power factor is always lagging? Then how come the motor current is leading the voltage? Here also there is a fault, so fault current must have been lagging. The problem is that motor is delivering the current and I am assuming the current is going into the motor. So actually the assumed direction and the actual direction of the motor current are opposite. And if you draw the opposite of a lagging phasor, what you will get will be a leading phasor. How? Suppose this is the voltage, this is your current, it is lagging the voltage. Now if you draw minus I, it is actually leading the voltage. So whenever you will commit an error in the direction of assumed current, you will observe that the fault current will lead the fault voltage. Okay. Why is it leading? Because the assumed direction is opposite to actual direction, which introduces a 180 degree phase shift. Hence the power factor goes from leading to lagging and vice versa. Let us see an example based on this concept. It is saying a 3-phase to ground fault takes place at location F1 and F2. If the fault takes place at location F1, then the voltage and current are at bus A are VF1 and IF1. If it takes at F2, it is at VF2 and IF2. We need to find the correct voltages, that is, which voltage will lead the current and which will lag. Now, as I told you, whenever the fault will occur, entire current will go into the fault like this. Okay, so first I am assuming at F1. Now take the bus A. Here IF1 and IF2 have been shown from left to right. But if you see, when the fault occurs at F1, the current at bus A is from right to left. That is, I assumed is equal to minus I actual. Both are in opposite directions. So here IF1 will lead VF1. Whenever the direction is opposite to the actual direction, the current will lead the voltage, or we can say VF1 will lag IF1. Now let us take the example of fault at F2. If fault occurs at F2, then current will go like this and this. So if you see at bus A, current is going from left to right. So IF2 assumed will be same as IF2 actual. Since both are same, the direction is correct. Hence IF2 will lag VF2, or we can say VF2 will lead IF2. Okay, so this will be the case whenever you will deal with the symmetrical short circuit fault. That is, if your assumed direction is opposite to the given direction, then the result will be leading power factor. If it is same as the actual, then it will be lagging power factor. Let us move on to the last problem. It is saying a sustained three-phase fault. Sustained means steady state. Occurs in power system shown in the figure. The current and voltage phasors are drawn on common reference after natural transients have died down. That is, we have reached steady state. We need to find the fault location. Now, as I told you, one thing to remember, the fault current will lead the fault voltage only if the direction shown and the direction actual are opposite. So here if you see, I2 leads V1 and V2. So that means I2 is shown opposite. I2 should go like this. Now we know all the currents should go into the fault. So let me first assume that the current fault occurs at P. So how will I1 be? I1 will go like this, I2 will also go like this. So now I2 satisfy the criteria that I2 should be from right to left, but I1 is from left to right and it is lagging the voltage, so that means direction is correct. Since I1 is lagging the voltage, that means the direction shown is same as the direction assumed, or direction shown is same as the actual direction. Hence I1 cannot be reversed, so P cannot be the fault location. If P were fault location, I1 as well as I2 will be reversed and both will be leading the voltage. Now assume that the fault is at R. Then the current will go like this. Okay. So I2 is in the same direction as shown. But just now we figured out since I2 is leading, it must be in opposite direction. So fault cannot be at R. If we talk about S, then how will the current go? Like this and like this. So here if you see, the current I4 will be reversed. Okay, if you talk about S, the current I4 is reversed, but as you see, I4 must remain as it is because it is lagging the voltage. So assumed direction or given direction is same as the actual direction. So last option that remains with us is Q. If fault occurs at Q, then I1 will go into the fault, I3 will go into the fault, I4 will go into the fault like this. So I2 direction is reversed. So it satisfies all the criteria that I2 direction is reversed and the entire current goes into the fault. And the other thing that you can observe is I1 has the highest magnitude. That is, fault must be located nearest to I1. Because the nearer the fault to a bus, the lesser the impedance and higher will be the fault current. So highest fault current has the fault nearest to the bus. So nearest to the bus V1 or 1 is point Q. So answer should be Q. Okay. So you have to observe two things. If any current or any fault current is leading the fault voltage, so assume direction or given direction is opposite to the actual, and if any current has the highest magnitude, so fault is nearest to that current location. So these two things will help you in non-trivial problems like this that can be asked in GATE. Other than that, the problems that can be framed is for finding the fault current. That is simple. You have to draw the equivalent circuit and then derive the fault current. So these sort of problems are generally framed from the symmetrical fault analysis. In the next lecture, we will start with unsymmetrical fault analysis and we will see how to deal with the unbalanced faults. Hi guys, up to now we have seen the analysis of symmetrical faults. In case of symmetrical faults, we considered two faults. One was line to line to line fault, other was line to line to ground. We said that line to ground fault is a special case of line to line fault where ZF will be 0. In this we derived the fault current in PU was 1 by Z1 equivalent plus ZF in PU. Z1 equivalent was the equivalent positive sequence impedance of the system. Here S was 1 by Z1 equivalent plus ZF PU, or it was also equal to S base by mod Z1 equivalent plus ZF PU. This will be in MVA. This will be in PU. Okay, so this was the short circuit MVA. Here we also saw how to select circuit breaker. We saw two rating. One was the maximum momentary current, which we were taking 1.6 into I symmetrical. Other we saw the breaking current, in which we took speed factor into I symmetrical. But while calculating symmetrical RMS current, we will considering transient reactance of a motor and subtransient reactance of a alternator. And then we were multiplying it by an empirical factor corresponding to the speed of operation of the circuit breaker, whether it is a 5-cycle circuit breaker, 2-cycle or 3-cycle circuit breaker. So that is what we have covered in the symmetrical fault analysis. In this lecture we will be starting with the unsymmetrical faults. Now first of all, what are unsymmetrical faults? These faults are not symmetrical. Not symmetrical in the sense they will not be same across all the three phases. So which faults will lie in this category? Line to ground fault. Here only one line is grounded, other two are same. Line to line fault, two lines get short circuited and the third line remains as it is. And line to ground fault. Okay, two lines are shorted and grounded and third one remains as it is. Now here, as you can see from the name itself, I can observe that the conditions pertaining to all the three lines or conditions persisting in all the three lines are not identical. Hence, this will make the system unbalanced. And since it will make the system unbalanced, we will require the method of symmetrical components. In case of symmetrical faults, symmetrical components is not that much required because only positive sequence will exist. But here symmetrical components is very important because it will make the system unbalanced. Okay. One assumption that we will consider while solving the unsymmetrical fault is no load before the fault. As we saw in case of symmetrical fault, we analyze both the no load as well as the loaded conditions, but here we will only analyze the no load condition. So let us get started with our first fault, that is your line to ground fault. Now here what I have assumed is that the phase A gets grounded and phase B and C will remain same. Now before fault what will be happening? We are considering no load condition. If before fault current is 0, that is no load, IA is equal to IB is equal to IC equal to 0, and all the voltages, that is VA, VB and VC, all will be balanced. How come they are balanced? Because they will be equal to EMFs, and as I told you, all EMFs are only positive sequence. If no current is flowing, VT will be equal to EF and they will be balanced. Now once the fault occurs, what will happen? IA will be non-zero as current will be flowing into the fault, but IB and IC will still remain 0 because no load is connected at B and C phase. And VA will become equal to IA into ZF. Just by KVL I am writing, here current IA is going into the fault, so the voltage will be IA into ZF. Okay, and VB and Vc will be unknown. So let us first analyze the components for the phase current. Okay. To know the configuration of the equivalent circuit, we must know the symmetrical components of current. So how to derive the symmetrical component in the currents? So we will find out IA0, IA1 and IA2. This will be equal to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. Current will be IA, IB is 0 and IC is also 0. Now from this matrix, IA0 will be equal to IA by 3. Similarly, IA1 will be equal to IA by 3, which is also equal to IA2. Okay, because IB and IC are 0. Now from here I can directly observe that all three sequence currents are same. Since current is only same in case of a series connection, so here sequence network will be connected in series. Okay. Earlier when we were studying sequence networks, then I told you we have to design separate sequence network for positive, negative as well as zero sequence. Now how those three networks will be connected together? They will be connected in series since the current through each network is identical. So how will my equivalent circuit look like? In case of positive sequence, we will show EMF as well as the equivalent impedance, because induced EMF is always positive sequence. In negative and zero sequence, there is no induced EMF, so only impedance is shown, Z2, Z0. And neutral impedance appears as 3 times the neutral impedance in the zero sequence circuit. We have connected it all together. Now VA was equal to IA into ZF, which is equal to IA will be equal to 3 IA1 into ZF or IA1 into 3ZF. That is why the fault impedance is shown as 3ZF, because the current flowing in the circuit is IA1, IA2 and IA0, which are all equal. So in terms of IA1, IA2 and IA0, the impedance offered to the current is 3 times ZF. So the fault impedance will also appear as 3ZF and the neutral impedance will appear as 3ZN. Now from this circuit, if we derive the sequence current IA1, it will be EMF upon total impedance. Impedance is Z1 plus Z2 plus Z0 plus 3ZN plus 3ZF. This is the positive sequence current flowing in the circuit. Now fault current is equal to current of phase A, which is equal to 3 times IA1, which is equal to 3 EA upon Z1 plus Z2 plus Z0 plus 3ZN plus 3ZF. Okay. This will be the fault current going into the fault at the phase A. Now, if we wish to find how much power is being transferred to the fault, that will be called as short circuit MVA. Now, in symmetrical component, what is the power? 3 times EA1, IA1 conjugate, EA2, IA2 conjugate, plus EA0, IA0 conjugate. Now since there is no EMF induced in negative and zero sequence, so this will be 0. So power will be actually 3 EA1, IA1 conjugate. Now this will be 3 times EA1 will be EA, IA1 is EA upon Z1 plus Z2 plus Z0 plus 3ZN plus 3ZF. Now EA into EA conjugate will be 3 into mod EA square by, if we talk about mod S, it will be mod z1 plus z2 plus z0 plus 3zn plus 3zf. Now if we wish to calculate this value in PU, I told you that we are assuming the no load condition before the fault occurrence. So no load condition signifies that induced EMF is equal to terminal voltage, which is equal to 1 angle 0. So S will be equal to 3 by mod Z1 plus Z2 plus Z0 plus 3Zn plus 3Zf in PU. This will be the short circuit MVA. If we wish to calculate this value in actual values, that is the MVA, so this value is in PU, it will be 3 into S base 3 phase by mod Z1 plus Z2 plus Z0 3Zn 3Zf in PU. This value will come out to be in MVA. So this is your short circuit MVA for the case of a line to ground fault. Now the most common mistake is this. Many people will forget this factor of 3 while evaluating the fault current or evaluating the short circuit MVA. So remember, this fault is different from a symmetrical fault as there is an additional factor of 3 in the numerator. Do not forget to consider this factor. The next fault that comes is line to line fault. So here what I have done is I have shorted the B and C phase with a fault impedance ZF. So ZF is my fault impedance and A phase is left as it is. Now since we are considering no load condition prior to the fault, that means IA, IB and IC were 0 before the fault. Okay. Now before the fault, voltages would be equal to EMFs, which is balanced. What happens when the fault occurs? When the fault occurs, since fault is occurring in B and C phase, the A phase will remain as it is. So IA will remain 0. But if we apply KCL here, IB is there, IC is there, IC will be equal to minus IB. And if we apply KVL between these two, VB minus VC will be equal to IF into ZF, or we can say IB into ZF. So these all equations we can derive from the network that is given to us. But our objective while analyzing the unsymmetrical faults is to derive the connection of the sequence networks. That is how positive, negative and zero sequence networks are connected together. That we have to figure out while analyzing the unsymmetrical fault. For that we must derive the sequence component of the fault current. Okay. So here we have to derive IA0, IA1 and IA2. This will be equal to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. IA is 0, IB is equal to IB, IC is equal to minus IB. Now from here if we calculate IA0, it will be 1 by 3, 0 plus IB minus IB, that is equal to 0. So 0 sequence current is 0. Hence 0 sequence circuit will be open circuited. So remember, whenever the ground is not present, that is in case of a line to line fault, what will happen is that the 0 sequence circuit will be open circuited or 0 sequence current will be 0. What about IA1? It will be 1 by 3, 0 plus alpha IB minus alpha square IB. That is IB by 3 alpha minus alpha square. Now alpha was equal to 1 angle 120. Alpha square is 1 angle minus 120. Now the resultant of these two will be how much? When two equal phasors are oriented at 120 degrees with respect to each other, the resultant will be, how much will it come out if we calculate from the phasor? It will be j by root 3 IB. Okay, because this resultant will be root 3 and it will become j by root 3 into IB. So this is my IA1. Now if we calculate IA2, it will be 1 by 3 0 plus alpha square IB minus alpha IB. So that is equal to IB by 3 alpha minus alpha square. That is equal to minus j by root 3 IB. Now, as you can observe here, IA2 is equal to minus of IA1. Okay, that, and here in this circuit was IC is equal to minus IB. So that means the connection of positive and negative sequence will be similar to the connection of B and C phase in this fault, because similar kind of relation we are obtaining for the sequence current. But if you see here, VB and VC have an impedance of ZF in between them. But we still do not know what will be the impedance between the positive and the negative sequence network. To determine that, we need sequence component of voltages. So to determine sequence component of voltages, VA0, VA1, VA2 will be equal to 1 by 3 1 1 1 1 alpha alpha square 1 alpha square alpha. Now VA is unknown, let us leave it as VA. VB is equal to VB, but VC is equal to VB minus IB into ZF. Okay, by KVL. So now if we wish to calculate VA1, VA1 will be 1 by 3 VA plus alpha VB plus alpha square VB minus alpha square IB ZF. And VA2 will be 1 by 3 VA plus alpha square VB plus alpha VB minus alpha IB ZF. Now to determine the impedance connected between positive and the negative sequence network, here this sort of relationship we had between VC and VB, so we have to subtract the voltages. So let me take VA1 minus VA2. Okay, so if we take VA1 minus VA2, this VA term will get cancelled out, alpha VB will get cancelled out, alpha square VB will get cancelled out. What will remain is 1 by 3 alpha minus alpha square IB ZF. Now alpha minus alpha square we just computed, it was equal to j root 3. So it will be equal to j by root 3 IB ZF. J by root 3 into IB was equal to IB1. So actually the relationship that is coming between VA1 and VA2 has the same impedance ZF in between the two networks. So how will my sequence network will look like? This one is my positive sequence. This one is your negative sequence. Here we haven't connected the zero sequence because zero sequence current is 0. Hence the zero sequence circuit is open circuited. And the impedance connected between the two networks is ZF. Now if you see here, IA1 is the positive sequence current and IA2 is the negative sequence current. This entire voltage will be VA1. This voltage will be VA2. So VA1 minus VA2 will be equal to IA1 into ZF as we derived here. So this will be actually IA1 because j by root 3 into IB was IA1. So IA1 into ZF, that is what we derived in the previous case. Okay. Just now we derived that VA1 minus VA2 should be equal to IA1 into ZF, and that can be derived from this circuit also. And this here is your reference bus. As you can see here also, the EMF only appears in the positive sequence circuit. No EMF is induced in the negative sequence. From this circuit, if we wish to calculate IA1, it will be EA by Z1 plus Z2 plus ZF. This is IA1. Now fault current, which is equal to IB, it is equal to minus J root 3 IA1, because IA1 was J by root 3 IB. So it will be minus J root 3 EA by Z1 plus Z2 plus ZF. So this will be the fault current in the system when a line-to-line fault occurs. Now if we wish to calculate the power that is being transferred to the fault, we will compute short circuit MVA. As I just told you, in three-phase symmetrical component, short circuit MVA is this. IA2 conjugate plus EA0 IA0 conjugate. Now we know that no EMF is induced in negative and zero sequence, so it will be equal to 3 EA1 IA1 conjugate, that is equal to 3 EA1 into EA1 conjugate by Z1 plus Z2 plus ZF conjugate, that is equal to 3 into mod EA1 square by Z1 plus Z2 plus ZF conjugate. Now if we wish to calculate magnitude only, it will be 3 mod EA1 square upon mod Z1 plus Z2 plus ZF. In PU it will be equal to 3, because EA1 will be 1 PU, mod Z1 plus Z2 plus ZF in PU. In actual values it will be 3 into S base 3 phase by mod Z1 plus Z2 plus ZF in PU. This whole value will be in MVA, whereas this value will be in PU. So this is how we calculate the short circuit MVA for a line to line fault. Okay. So remember here that the short circuit MVA also consists of a term 3 in case of unsymmetrical fault. Okay. There it was only 1 by Z1. The next fault that comes is double line to ground fault or line to ground fault. Here what we have done is we have shorted B and C phase and then we have connected it to ground by a fault impedance ZF. Now again here first we will consider the before fault condition. Before fault there was no load on the system. So IA is equal to IB is equal to IC equal to 0. VA, VB, VC are all balanced. Now when the fault occurs, what will happen is, since A phase is unaffected, it will remain 0, but here IB and IC will not be equal to 0, and here the fault current, the current going into the ground is equal to actually IB plus IC. Since B and C phase are shorted, VB will be equal to VC, whereas VA will be unknown. Okay, and VB is equal to VC, and VB is equal to VC is equal to how much? IF into ZF, which is equal to IB plus IC into ZF, or what I can write is IA plus IB plus IC into ZF, because IA is 0 anyways, and we know the sum of the three currents is equal to 3 IA0 into ZF. So this will be the voltage of the faulty phase, that is VB and VC, that is equal to 3 IA0 into ZF. Now to derive what is the connection of the sequence networks for a double line to ground fault, we will derive the symmetrical component of currents. So to derive symmetrical component of currents, we will calculate IA0, IA1 IA2, which is equal to 1 by 3 1 1 1 1 alpha alpha square 1 alpha square alpha. Here the current will be IA0 is IA is 0, IB and IC. Now if we calculate IA0, it is equal to 1 by 3 IB plus IC. IA1 will be equal to 1 by 3 alpha IB plus alpha square IC. IA2 will be equal to 1 by 3 alpha square IB plus alpha IC. Okay. So this will be your sequence component of the fault current. And here, since the fault current IF is equal to IB plus IC, it will be equal to 3 times IA0. So whenever in case of a double line to ground fault, you have been asked about the fault current, you will calculate 3 times the zero sequence current. But still from here it is not very clear as to what will be the connection of sequence network. And from here I can observe one more fact is, since IA is 0, what will happen is IA0 plus IA1 plus IA2 must be 0. That is, these currents should be like this: IA0, IA1, then IA2. So somehow the sequence network should be connected like this, so that all the currents are converging to the same point and their sum will become 0. So this gives us a hint of what should be the connection of the sequence network. To be more clear what is the connection of the sequence networks, we will derive the sequence component of voltages. To derive sequence component of voltages, what we will take is VA0, VA1, VA2 will be equal to 1 by 3 1 1 1 1 alpha alpha square 1 alpha square alpha. VA is unknown, it is VA. VB is equal to VB. VC is also equal to VB. So VA0 is 1 by 3 VA plus 2 VB. VA1 will be equal to 1 by 3 VA plus alpha square VB plus alpha VB, or it can be written as 1 by 3 VA minus VB. How come VA minus VB? Because alpha plus alpha square is minus 1 because of this property. VA2 will be 1 by 3 VA plus alpha square VB plus alpha VB, which is equal to 1 by 3 VA minus VB. Now from here, if you see, positive and the negative sequence voltages are equal. If these voltages are equal, then what will happen is these networks will be connected in parallel. But zero sequence and the positive negative sequence voltages are unequal. So to derive what is the voltage difference between them, what we will take is, we will just subtract VA0 and VA1. How much will this come out to be? 1 by 3. VA minus VA will get cancelled out, and 2 VB minus VB is 3 VB. So this will come out to be how much? It will come out to be VB, which is equal to IF into ZF, or we can say 3 IA0 ZF, or we can say IA0 into 3 ZF. Now based on the facts that we have derived in this sequence component of voltage and current, let us draw the sequence network. So here positive and negative sequence networks are connected in parallel because we derived VA1 is equal to VA2. But if you see here, current IA0 is flowing in the zero sequence network. By KCL, IA0 will flow here. So if we apply KVL, VA0 minus VA2 will be equal to 3 IA0 into ZF, because impedance is 3 ZF. That is what we derived in the last slide, that VA0 minus VA1 was 3 IA0 into ZF. and VA1 and VA2 are identical, so VA0 minus VA2 should also be 3IA0 into ZF. So we will connect the impedance 3ZF between the 0 sequence and the positive negative sequence. So this is the equivalent circuit, and this here is my reference bus. Now to derive the fault current here, first we will calculate IA1. IA1 will be EA by Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF. Okay, this will be IA1, but we know fault current is equal to 3IA0. So to calculate IA0, what we will do is IA1 is going here, so it will get divided into minus IA2 and minus IA0. Why I am telling minus IA2 and minus IA0? Because the indicated direction of IA2 and IA0 are opposite to the actual current. So IA0 will be equal to minus IA1 into current division. Current division will be Z2 over Z2 plus Z0 plus 3Zn plus 3ZF. Okay, so this way we can calculate IA0, and then 3 times IA0 will yield the fault current. Okay, so this is the method of calculating the fault current in case of a double line to ground fault. But remember, in all these cases, that whatever impedances we are taking, they should be in per unit. Okay, usually this analysis is done in PU. You can take in ohms, but then you have to remember that this EA represents the per phase voltage. Okay, so it is better that you solve it in PU, because that will simplify a whole lot of effort. Okay, and remember, fault current is 3 times IA0, and it is not related to IA1 directly. In line to ground fault, fault current was equal to 3 times IA1, and in double line to ground fault, it is 3 times IA0. Now to derive the short circuit MVA, or the power being transferred into the fault, again I am directly writing now 3 EA1 IA1 conjugate, because EA2 and EA0 are 0. That is 3 EA1. IA1 conjugate will be EA1 conjugate by Z1 plus Z2 plus Z2 parallel Z0 plus 3Zn plus 3ZF. Now EA1 into EA1 conjugate, it will be mod EA1 square by Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF. Okay, in PU if we calculate, it will be EA will be taken as 1 PU, because of no load condition EA will be equal to VT. Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF in PU. In MVA it will be 3 into S base 3 phase by mod Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF in PU. This will give the result in MVA. So this is my short circuit MVA for the case of double line to ground fault. Now if we compare the fault or the short circuit MVA, then what will happen is, in case of LG fault, what it was, 3 by Z1 plus Z2 plus Z0 plus 3 Zn plus 3 ZF. In case of LL, it was 3 by mod Z1 plus Z2 plus ZF. So there was no trace of Z0. In LLG, it is 3 by mod Z1 plus Z2 parallel with Z0 plus 3Zn plus 3ZF. Now if you see the denominator of all these three terms, in this Z1, Z2 and all the impedances are connected in series. So this impedance will be highest and this will be lowest. Okay. And in this case, what will happen is, Here we have only Z1, Z2 and ZF, and Z0 is not there. So this will be higher. And here if you see, Z2 is in parallel with this impedance. Now whenever you connect two impedances in parallel, the resultant is less than either of the value. That is, it will be less than Z2 as well as less than this value. So this value is actually less than Z1 plus Z2. So this value is least, and thus the LLG fault has the highest MVA. But if you consider the symmetrical fault, it was 1 by Z1, or we can say 3 by 3Z1. So it is actually maximum. Why maximum? Because Z0 will always be greater than Z1 Z2. Why? Because of the transmission line in the system. Whenever you will have transmission line, Z0 for a transmission line is actually 3 times the positive or the negative sequence impedance. Since Z0 is very high, that is why the symmetrical fault or a triple line fault will have the maximum short circuit MVA, because the denominator will be minimum. But now suppose I eliminate transmission line from the system. How? I can say that the fault is occurring at the terminals of generator. Then transmission line actually does not come into the picture. And as far as we know, for a generator, what happens is Z1 is greater than Z2 is greater than Z0. So Z0 is actually minimum. So this order will be reversed and LG fault will be most severe, or it will have the maximum short circuit MVA. So remember, whenever the fault will occur in a transmission line, symmetrical fault is most severe. If the fault occurs at the terminals of generator, LG fault will be the most severe. So it is not universally true that the symmetrical faults are more severe as compared to unsymmetrical fault. Why is this happening? Because in case of transmission line, zero sequence impedance is highest, which will reduce the fault current. But if fault occurs before the transmission line, then zero sequence impedance does not come into play, and the fault current will be higher for the case of line to ground fault. So do remember this concept, so that if there is a statement that says that the triple line fault is the most severe fault, that is not universally true. It is false, because whenever the fault will occur at the generator, LG will be most severe. So let us summarize what we have covered in the fault analysis. Whatever faults we have seen is, we have seen 4 types of fault. One is the symmetrical and the 3 types of unsymmetrical faults. Then what are the currents? Then sequence voltage. Then let us say short circuit MVA. Okay. First fault that we consider is LG fault. What was happening? IA1 was equal to IA2 was equal to IA0. All networks were in series. And here the sequence voltage VA was equal to VA1 plus VA2 plus VA0, which was equal to IA into ZF. And short circuit MVA was 3 by mod Z1 plus Z2 plus Z0 plus 3ZF plus 3Zn in PU. Okay, so just remember the short circuit MVA expression in case of PU. And fault current in this case was equal to 3 times IA0. That was for the case of LG fault. Now what will happen for the case of line to line fault? In case of line to line fault, we saw that the ground was missing. So IA0 is equal to 0 and IA1 plus IA2 was equal to 0. What happened to sequence voltages? VA1 is equal to VA2. Both were in parallel. What was happening to short circuit MVA? Mod Z1 plus Z2 plus ZF in PU. And what was the fault current? Fault current was equal to minus J root 3 into IA1. Then double line to ground fault. All networks were in parallel. So IA0 plus IA1 plus IA2 was equal to 0. What happened to voltages? VA1 was equal to VA2. Okay. Here actually VA1 was not equal to VA2. VA1 minus VA2 was IA1 into ZF, because ZF was the impedance between the two circuit. Here VA1 was equal to VA2 and VA0 minus VA1 was 3IA0 into ZF. And what happened to the short circuit MVA? The short circuit MVA for a double LG fault was 3 by mod Z1 plus Z2 parallel with Z0 plus 3Zn plus 3ZF in PU. What was the fault current? It was equal to 3 times IA0. So that is actually the line to ground fault. And what happened to the symmetrical fault? That is, if we consider triple L fault, sequence current only IA1 was non-zero. Negative sequence and zero sequence did not exist because it was a balanced fault. Okay. And here, in case of this, only VA1 was non-zero. Again, negative and zero sequence voltages were 0. What was the short circuit MVA? 1 upon mod Z1 in PU. And what was the fault current? It was equal to IA1 because only positive sequence was flowing in the system. So these are 4 types of faults that we have covered. Out of this, one is symmetrical and other 3 are unsymmetrical. What you have to remember in case of unsymmetrical faults is, you have to remember the fault current, short circuit MVA and the equivalent circuit of each of the fault. If you remember the equivalent circuit, most of the problems you can solve directly. And remember some salient features of each type of fault, like in a line-to-line fault, zero sequence current is 0. So whenever there is no ground in the fault, then zero sequence current cannot flow. So in case of ungrounded fault, zero sequence currents are always 0. Okay. In the next lecture, we will study about the importance of neutral grounding. Why is it important to ground the neutral to save the system from any damage? That we will cover in the next lecture. Hi guys, in the last lecture we saw case of unsymmetrical faults. In unsymmetrical faults, the first fault that we saw was LG fault. In this fault, all the sequence networks were connected in series, and we saw that fault current was equal to 3 times IA1, where IA1 was equal to EA by Z1 plus Z2 plus Z0 plus 3Zn plus 3ZF. And the short circuit MVA was mod Z1 plus mod Z2 plus Z0 plus 3Zn plus 3ZF. Okay, in PU. This gives the short circuit MVA in PU. Now S into S base 3 phase will give me short circuit MVA in the units of MVA. So this was for the case of LG fault. Similarly, the next type of fault that we saw was double L fault or a line-to-line fault. In this we saw fault current was actually equal to minus J root 3 IA1. IA1 was equal to EA1 by mod Z1 plus Z2 plus ZF. Okay. And the short circuit MVA was 3 by mod Z1 plus Z2 plus ZF in PU. And S into S base 3 phase will give me short circuit MVA in units of MVA. The next type of fault that we saw was double line to ground fault. In this we saw the fault current was equal to 3 times IA0. We calculated IA1 as EA1 by Z1 plus Z2 in parallel with Z0 plus 3Zn plus 3ZF. And here IA0 was minus IA1 into Z2 by Z2 plus Z0 plus 3Zn plus 3ZF. And short circuit MVA we calculated as 3 by Z1 plus Z2 parallel Z0 plus 3Zn plus 3ZF in PU. Similarly, if we multiply it by the base value, we will get the short circuit MVA in the units of MVA. And we also studied that the most severe type of fault is the symmetrical fault. If the fault occurs on the transmission line, and it is the LG fault which is most severe if the fault occurs at the terminals of generator. Okay, so let us first get started with the problem based on a LG fault. Now it is saying a star connected alternator with isolated neutral. Isolated neutral means Zn is infinity, has positive, negative and zero sequence impedance as J.18, J.12, J.06 respectively. So here there must be a J. Rating of alternator is 100 MVA 18 kV when a LG fault occurs on phase A on no load alternator. Now first of all, it is given no load, so EMF will be 1 angle 0. Now if we draw the equivalent circuit, all the sequences will be connected in series, positive, negative, then 0, then the neutral impedance is actually infinity, so it will be open circuited. And since ZF is not given, I will take it to be 0. So this is J.18, J.12, J.06. Okay, this is open circuited here because Zn is infinite. Now here, since it is open circuited, all the sequence currents will be 0, due to which the positive sequence voltage VA1 is actually EA1 minus IA1 into Z1 will be equal to 1 angle 0. VA2 is actually minus IA2 into Z2. This will also be 0. Now VA0, we know since A phase is faulted, VA1 plus VA2, because VA1 plus VA0 plus VA2 must be 0. In case of LG fault, VA is equal to IA into ZF, but here ZF is 0, so VA must be 0. Hence VA0 plus VA1 plus VA2 must be 0. So VA0 must be minus 1. So now we know the sequence component of the voltages. We can calculate VB and VC. So VB is actually how much? VA0 plus alpha square VA1 plus alpha VA2. So VA0 is minus 1. Alpha square VA1 is 1 angle 240 into 1. VA2 is 0. So this will come out to be root 3 angle minus 150 degree PU. VC will be VA0 plus alpha VA1 plus alpha square VA2 minus 0, 1 angle 120, VA1 is 1. plus 0. So it will come out to be root 3 angle 150 degree pu. So here if you see, the phase voltage magnitude is coming to be root 3 per unit. So its actual value will be per unit value multiplied by base. Now base for the phase voltage will be line voltage by root 3. So it will be equal to 18 kV. So now if you see here, the phase voltage magnitude becomes equal to line voltage if the neutral of the system is left isolated. That means high voltage will be induced in the transmission line if you do not ground the neutral of the system. That is why we need neutral grounding to avoid high voltages. So ungrounded neutral has high voltage. Now when the voltage of the conductor is high, suppose we take the case of our overhead line. If the voltage of the conductor is high, then what will happen? The air around this will ionize. So there will be an arc formation. If arc is formed, then it is called as arcing fault. Current will flow into the tower through the arc. That is called as arcing fault or a arcing ground. If you do not isolate the neutral, an arc can be formed along the insulator, which is also known by the term as insulator flashover. Okay, so these type of fault are called as arcing ground. That is why these are dangerous. The only advantage of isolated neutral is that the circuit or the equivalent circuit that we saw was open circuited. So zero sequence current will be 0. Okay, if Zn is infinity, Ia0 will always be 0. So no radio interference, because as I told you, in case of an unbalanced system, the radio interference is only due to the zero sequence current, and hence there will be no radio interference. But the danger is the danger of an arc formation due to isolated neutral. Okay. The other danger is due to the high line charging current. Let us see how. Suppose this system is given to me. This system is under no load. Under no load, in case of a transmission line, line charging currents will flow and they will be represented by capacitance of the line ZAG, ZBG and ZCG. Now, when there is no fault, that is, we are considering the condition before the fault, all the three voltages will be balanced: VA, VB, VC, and the line charging current will lead the voltage by 90 degree. So this will be IA, then IB will be leading the VB by 90 degree, IB, and then this will be IC, like this. Okay, so these will be the line charging current. IA is equal to IB is equal to IC is equal to I charging. Okay, but what happens when the fault occurs? When the fault will occur, this phase gets grounded. So earlier the current was omega C phase V phase, but let us see now what happens to the line charging current in case one line to ground fault occurs. Here, as I have shown, the neutral is left isolated. Now suppose this phase is connected to ground. So what will be the voltage of VB, or we can say VBG? VBG will be actually VBC plus VCG. Now since C phase is directly connected to ground, VCG is 0, C is grounded. So voltage of B phase with respect to ground is VBC. Similarly, voltage of A phase with respect to ground will be VAC. That is what we saw in the previous example also. The phase voltage will become equal to line voltage in case of a line to ground fault with isolated neutral. Okay, or the magnitude of phase voltage becomes root 3 times. So what will happen is, these are my balance voltages VA, VB and VC. Now what will happen is, VA will become equal to VAC, VB will become equal to VBC. So the line charging current in phase A will now be perpendicular to VAC. It will be like this, IA. Similarly, IB will be perpendicular to VBC. This will be IB. And the sum of these two currents will give me total line charging current, which is like this, I. Now first of all, VAC will be equal to root 3 VA. So IA, which will be equal to omega C phase into VA, will be equal to omega C phase root 3 VA. Or we can say VAG. VAG is now becoming equal to VAC, which is root 3 VA. Because phase voltage becomes equal to line voltage. So it becomes equal to root 3 times the initial line charging current. Now angle of these two currents is 60 degree. So the resultant is actually root 3 times the individual vector. Here IA is equal to IB is equal to root 3 times I charging, and the resultant I will be equal to root 3 IA, which is equal to 3 times I charging. So 3 times the line charging current will flow if the neutral is left ungrounded. How it will flow? It will flow in phase A and B, and it will come through the phase C. This I charging current is equal to IA and IB. So very high current will flow through the C phase winding if the neutral is left ungrounded. Okay, and the system voltage or the phase voltage will become equal to line voltage, due to which arc will be formed. Hence we have seen the two type of disadvantages when the neutral is left ungrounded. High line charging current flows and the system voltage becomes dangerously high. So let us discuss how we can ground the system. So grounding methods are basically divided into two parts. One is called as system grounding, other is called as neutral grounding. Now first of all, what is meant by system grounding? Okay, or these two terms are actually same, system or neutral grounding. This is called as, next is equipment grounding. So first of all, what is meant by system or the neutral grounding? Neutral grounding means that we will ground the neutral of a system in order to stabilize the system. Otherwise, phase voltage magnitude becomes equal to line voltage, due to which there is a formation of arcing, or there is a formation of arc, due to which it is called as arcing fault. To avoid the formation of arc or arcing faults, we have to connect the neutral to the ground. Otherwise, the system may get damaged. Okay, so it is to protect the system from getting damaged due to dangerously high voltages. Then what is meant by equipment grounding? It means grounding the outer body of the equipment. Now why would we want to ground the outer body? Because there are certain stored charges on the body of every equipment. If there are stored charges, then what will happen? Whenever we will touch the equipment, those stored charges will flow through to the ground through our body. If those charges are flowing to the ground through our body, then we may get a shock. So to avoid that shock, we need to provide a path for the flow of those stored charges to the ground. That is done by equipment grounding, which is also called as earthing. Okay, so this is the basic difference between the grounding and the earthing. Grounding term refers to grounding the neutral of a system to avoid any system damage due to high voltage, And earthing refers to grounding the outer body of the equipment to release the stored charges into the ground, or to provide a low resistance path for the flow of charge into the ground that will protect the operator of the equipment from any shock. So these two type of grounding methods are generally used. Our focus will be on the system or the neutral grounding. So let us see what are the various types in which we can ground the neutral of a system. First one is called as solid grounding. That is, you will directly connect the neutral to the ground. There is no neutral impedance, that is Zn is 0. That is called as solid grounding. Now how to decide when you will have to use the solid grounding? If zero sequence reactance upon positive sequence reactance of the system is less than 3, we use the solid grounding. Okay. So this is the criteria for the case of solid grounding. The next type of method is called as resistance grounding. Here what you will do is you will ground the neutral by means of a resistance. So here Zn is equal to Rn. Now where to use this type of grounding is, it is used where charging current IC is small. Why? Because as we saw, if the neutral is left ungrounded, high line charging current are induced. There IC was becoming equal to 3 times I charging. But if I charging is small, then IC is small. Then we can use a resistance. Otherwise, if I charging is high, IC will be high. We will need an inductor to cancel the capacitor current. But if the current is small, we can do with a resistance. Okay. Resistance is not meant to cancel this current because only an inductive current can cancel a capacitive current. But what happens is that, as we will study later on, Rn improves stability of a system. And in case of synchronous generator, which are mostly used in our power plant, stability is one of the most important criteria. That is why resistance grounding will be mostly used in case of alternators. Okay. It can only be used where the line charging current is small, like the case of short transmission line, because there we neglect the line charging current. There you can use resistance grounding and it will improve the stability of the system, but it cannot cancel the line charging current. Now if you have to cancel the line charging current, you will have to use reactance grounding. That is, neutral will be grounded by means of a reactance Xn. So here Zn will be equal to J times Xn. It will be purely imaginary. That is the neutral impedance. Here X0 by X1 should be greater than 3 for the use of reactance grounding. Where to use reactance grounding? Wherever the line charging current is high. Where will the line charging current be high? It will be high for the case of long transmission line, capacitor bank, synchronous motor, because synchronous motor is usually operated at a leading power factor, so it will act as a capacitor. So whenever there the system has having capacitor, line charging current will be high, we have to use the reactance grounding. The next method is called as Peterson coil, or the case of resonance grounding. Resonance means whenever the inductance cancels the effect of capacitance completely, system is said to be under resonance. Okay. So here also we are using reactance grounding, but the reactance is chosen such that it cancels the effect of capacitance or the line charging current. We just now saw whenever there is a line to ground fault, whatever the current is flowing in this wire, it is equal to 3 times I charging. Okay. That was being divided into the two phases. Here I have grounded the A phase. So IA will be equal to 3 times I charging. When we were doing the derivation, then we were grounding the C phase. So C phase current was coming out to be 3 times I charging. Now this current should be cancelled out by this IL. So IL is actually V phase by XL. It should be equal to 3 times I charging, which is equal to 3 omega C phase V phase. Okay, 3 times I charging we derived earlier only. It should be equal to V phase by omega L. So here L will be equal to 1 by 3 omega square C. This is the inductance that you have to use for the case of resonance grounding or for the case of Peterson coil. This is also called as inductance of the arc suppressor coil, because if you use this inductance, then the line charging current will get cancelled out. There will be no formation of arc. So arc is suppressed here. So it is also called as arc suppressor coil. Inductance of arc suppressor coil is 1 by 3 omega square C. So these are the general methods by which we will ground the neutral of a system. That is, one was solid grounding, other was your resistance grounding, reactance grounding, then Peterson coil. Peterson coil is a special case of reactance grounding in which the inductance is equal to 1 by 3 omega square C. So let us summarize what we covered in this lecture. We first saw the case of isolated neutral and we saw two disadvantages. One was phase voltage became equal to line, and one was the 3 times line charging current flowing through the grounded phase. Then we saw the grounding method, which was system grounding and equipment grounding. System grounding was also called as neutral grounding. We were grounding the neutral to avoid high voltages. And in equipment grounding, we were grounding the outer body to provide a low resistance path to the flow of stored charges. Then we saw the methods of neutral grounding. We first saw solid grounding, which will be used if x0 by x1 is less than 3. Then we saw resistance grounding, which is used in alternators to improve the stability, and it is used where I charging is small. Then we saw reactance grounding. It is used where IC is large, which will be the case when we will be using synchronous motor or capacitor bank. Then we saw the arc suppressor coil or the Peterson coil, which was 1 by 3 omega square C, which will completely suppress the arc as it will cancel the line charging current. So these are the following methods of the neutral grounding. In the next lecture, what we will do is we will consider the problems based on unsymmetrical faults and analyze how or understand how to analyze the unsymmetrical faults. That will be done in the next lecture. Hi guys, up to now we have seen different type of fault and what is the fault current and what is the fault MVA for symmetrical as well as unsymmetrical type of faults. In symmetrical we have seen triple L fault and triple LG faults. In unsymmetrical we have seen LG, LL and LLG type of fault. So in this lecture what we will do is we will focus our attention to solving few problems that have been based on unsymmetrical type of faults, so as to get to know better how to tackle such kind of problems. So let us get started with our first problem. It is saying it is given that Vs1 is equal to Vs2 1 plus J0. Okay, that means Vs1 is equal to Vs2, that is 1 angle 0. Then positive sequence impedance Zs1, Zs2 are 0.001 plus 0.01. ZL is 0.006, J 0.06, base MVA 100, base voltage 400. Nominal system frequency is 50 Hz. Now VA is given as reference voltage for phase A, Vm cos omega t. A symmetrical three-phase fault occurs at center of the line I at point F at time t0. The positive sequence impedance from S1 to F equals this. Okay. Since fault is occurring at the midpoint, the impedance of the line will be taken as ZL by 2. That is 0.003 plus J 0.03 pu. And let me show you the diagram. Fault is occurring here. And the impedance from source 1 to F will be ZS1 plus ZL by 2. ZS1 plus ZL by 2 will be 0.004 plus J 0.04 pu, which is given in the question also. The waveform corresponding to phase A fault current from bus X reveals a decaying DC offset current. Okay. The thing is, whenever we will study about the fault current, there are two components, transient and a steady state. It is saying the waveform has a DC offset current that is negative. So this is actually transient current and in magnitude at its maximum initial value. So magnitude is maximum, but the value is negative. Assume negative sequence are equal to positive sequence impedance. Zero sequence is 3 times positive sequence. Z2 is equal to Z1. Z0 is given as 3Z1. First question it is asking what is the instant of the fault. Now for transient and steady state we derived the current as IT0 e raised power minus RT by L plus Vm by mod Z. Here it will be cos of omega t minus theta. Theta will be tan inverse x by r, that is 0.04 by 0.004, which will be 84.29 degree. Now at t is equal to t0, when the fault is occurring, IT must be 0 due to current continuity. We are assuming no load condition in the system before the fault occurrence. So IT0 e raised power minus RT0 by L will be equal to minus Vm by mod Z cos of omega t0 minus theta. Now this is the decaying DC offset current. It must be negative, so negative sign is coming here, and equal to maximum initial value. For maximum value, the maximum value of this current will be Vm by mod Z, because cos can be 1. So this should be equal to minus Vm by mod Z, which implies that the term inside the cos should be equal to 0, because cos must be equal to 1. That means omega t0 must be equal to theta. So t0 will be theta by omega. 84.29 into pi by 180, whereas omega will be 2 into pi into 50. So this will come out to be how much if we calculate 4.682 millisecond. So this will be the instant of the fault. Okay. So what the case that we considered while deriving it was the fault was occurring at t is equal to 0. But here we have seen a general case, the fault occurs at t is equal to t0. Okay. So just you have to decode the language and nothing else, though the question seems a bit bigger, but the solution is not that much tricky. The next part of the same problem asks us to find the RMS value of AC component of fault current Ix. Okay. RMS value of AC component, that is symmetrical fault current. Now RMS value will be V by mod Z. Okay, V is how much? First we will take 1 angle 0 because of no load condition. Mod Z is 0.004 plus J 0.04. Why I am not taking the equivalent of this and this? Because what will happen is it is only asking about Ix. Ix will be supplied by Vs1. Okay. If it were asking about If, If is actually 2 times Ix because If is Ix plus Iy, which both will be equal. Why both will be equal? Because system is identical here and here. Both the systems are identical. Since it is asking only about Ix, so I am calculating Ix. Okay. So this will come out to be 24.9 angle minus 84.29. Now if we have to calculate in actual values, we have to multiply it by base current. So 24.9 into base will be MVA base by root 3 into voltage base. So this will come out to be 3.59 kiloampere. That is your RMS value of fault current. In the next part of the same problem, it is saying instead of three-phase fault, a single line to ground fault occurs at point F on phase A with zero fault impedance. Okay, zero fault impedance signifies ZF is 0. Okay, we need to find RMS value of fault current Ix. It will be 1 by, in case of LG fault it is 3 by mod Z1 plus Z2 plus Z0. Okay, because Zn is also 0, solidly grounded. ZF is also 0. Now it was given Z1 was 0.04. Okay, because in case of symmetrical fault we only consider the positive sequence impedance. Z2 was given equal to Z1, that is okay, and Z0 was given as 3Z1, that is 0.012 plus J.12 pu. Now if we compute the Ix, it will be 5 times Z1 0.004 plus J.04. So how much will this come out to be? This will come out to be 14.925. Let us say 14.92 pu. To calculate the actual value, we will multiply it by base value, that is equal to 100 by root 3 into 400. Okay, so this comes out to be 2.15 kiloampere. So that is the fault current for the case of a LG fault. Now clearly here current of LG fault is much less than triple L fault. So it is the case where symmetrical fault is the most severe type of fault. Why? Because fault is occurring at the transmission line. Okay, if fault were occurring at the generator terminals, then LG fault will be the most severe type of fault. Moving on to the next problem. It is saying at a 220 kilovolt substation of a power system, it is given three-phase fault level MVA is 4000 MVA and SLG fault level is 5000 MVA. So clearly here I can see that MVA of the SLG fault is more than 3-phase fault. So line to ground fault is most severe in this case. Now if we neglect all the resistance and susceptance of the system, we need to find positive sequence driving point impedance. Now we know for a 3-phase fault or a symmetrical fault, short circuit MVA is actually S base upon mod Z1 in PU. Now S base can be written as V line to line square by Z base that is VL square by Z1 in ohm. Okay. So this can be the other formula for short circuit MVA. So here I am considering in terms of voltage because we are given the voltage and not the base MVA. So if we equate it, 4000 will be equal to 220 square by Z1. From here Z1 will come out to be 12.1 ohm. Okay. This will be the positive sequence impedance for the bus or for the case of fault. Okay. In the next part of the same problem, it is asking the zero sequence reactance. Now, whenever we have three impedances, let us say Z1, Z2 and Z0. But we have only two equations. One equation is for triple LG fault, other is for LG fault. So we have two equations and we have three variables. So what to do in such a case is, you will assume that Z1 is equal to Z2. Okay. If ever you fall into such a place that there are three impedances and only two equations, you will assume positive and negative sequence as equal. So this will be equal to 12.1 ohm. Now we know the short circuit MVA for LG fault is 3 into S base by mod Z1 plus Z2 plus Z0 in PU. Again replace S base by VLL square by Z base into Z base. So this will be 3 VL square by mod Z1 plus Z2 plus Z0 ohm. So it will be 3 into VL is 220 square by 24.2 plus Z0, which will be equal to 4000. So from here Z0 comes out to be 4.84 ohm. Okay. So this will be the zero sequence impedance. From here you can also see that Z1 is equal to Z2 is greater than Z0. So this is the case of a generator. Hence the line to ground fault is more severe as compared to your triple L or the symmetrical fault. I told you symmetrical fault is most severe when fault occurs on a transmission line because zero sequence impedance is high. Here zero sequence impedance is low, due to which LG fault is most severe. In our next problem it is saying a 500 MVA 50 Hz 3-phase turbo generator produces power at 22 kV. Generator is star connected and neutral is solidly grounded. So Zn is 0. Its sequence reactance X1, X2 and X0 are given. It is operating at rated voltage and disconnected from rest of the system. We need to find subtransient line current for SLG fault. Now I symmetrical will be 3 by mod Z1 plus Z2 plus Z0, that is 3 by 0.15 plus 0.15 plus 0.05. Here 3 Zn will be 0 because Zn is 0. So it will be 3 by 0.35. So how much will this come out to be? This comes out to be 8.57 pu. This is the subtransient line current for the case of SLG fault. Okay, just keep in mind to maintain a factor of 3 here. In our next problem, it is saying a 20 MVA 6.6 kV 3-phase alternator is connected to 3-phase transmission line. Okay, so this is alternator, this is your 3-phase transmission line. Now positive, negative and zero sequence reactance of alternator are given. Positive, negative, 0. For generator it is 0.1, 0.1, 0.04. Neutral of the generator is connected to a ground through a inductive reactor J.05. So Zn is J.05. Okay. For transmission line, positive, negative and zero sequence are 0.1, 0.1 and 0.3. As you can see, Z1 equal to Z2 and Z0 is 3 times Z1. All PU values are based on machine rating. A SLG fault occurs at the far end of the transmission line. We need to find voltage of alternator neutral with respect to ground. Now alternator neutral voltage will be I neutral into Z neutral. I neutral is actually 3 IA0 into Zn. So we have to compute IA0. For the case of SLG fault, IA1 is equal to IA2 is equal to IA0, which is equal to 3 by Z1 plus Z2 plus Z0 plus 3 Zn. Now Z1 for the system will be Z1 generator plus Z1 line. Since both are connected in series, their respective sequence impedance will be added. So it will come out to be J.2 pu. You have to separately form the sequence network for each sequence. Z2 generator plus Z2 line. So it will come out to be J.2 pu. Now Z0 equivalent will be Z0 generator plus Z0 line plus 3 Zn. So it will be 0.04 plus 0.3 plus 3 into 0.05. So it will be J.49 pu. So from here IA0 will be 3 by J.2, 0.2, 0.49. So how much will this IA0 come out to be? IA0 will be only this much, 1. So it will be 1 by 0.89. It will be 1.123 pu. Now if we wish to calculate the neutral voltage, Vn will be 3 into 1.12 into 0.05. So 0.15 into 1.12 will be 0.168 pu. To calculate the actual value, we will multiply it by the base. Vn will be 0.168 into 6600 by root 3, which will be 640.18 volt. So here we have to take the phase voltage base value because it is not the line to line voltage, rather the neutral voltage. In next problem it is saying the severity of LG fault and 3-phase fault at the terminals of unloaded synchronous generator is to be same. Severity is same means IF LG must be equal to IF triple L. If terminal voltage is 1 pu, Z1 and Z2 and Z0 are given, we need to find the reactance for neutral grounding. Now this will be equal to plus 3 Zn, and in case of triple L it will be 1 by Z1. So how much is this? 0.25 plus 3Zn 1 by 0.1. So here Zn will be, it will be 0.05 by 3, that is 0.0166 pu. That will be your reactance or the impedance for the neutral grounding to make LG as well as triple L fault having the same severity level. Okay. Otherwise, triple L fault will be more severe as compared to your LG fault. In our last problem, it is saying for the system shown in the diagram given above, what is the line to ground fault on line side of transformer equivalent to? So here it is saying that LG fault is occurring. We have to see the fault here, or we have to refer the fault here. What will be the nature of fault? Now, if you see, this is a delta star type of transformer. In delta star grounded, what is the zero sequence circuit? Here we will keep open the series switch. It is like this. So zero sequence current can flow on the star side, but it cannot flow in the lines of delta. So if you see from the generator side, it will appear that there are no zero sequence current, and IA0 is 0 only for the case of line to line fault. So from generator perspective, it will seem that the line to line fault has occurred in the system, due to which no zero sequence currents are flowing. Hence, if we refer the LG fault on the generator side, it will become line to line fault. Okay. So here you just have to observe the sequence currents from the generator side. Okay. Based on the sequence current on generator side, we can judge the type of fault. So such kind of questions can also be framed, which will relate different type of faults. Okay. So only these kind of questions are generally asked from unsymmetrical fault, that is for computation of fault current. And for symmetrical, two type of problems. Ones are conceptual, in which we will be given phasor diagrams, location of fault, and ones are numerical, in which we have to find the symmetrical fault current. So these are the few type of problems that can be framed from this topic. Okay. In the next unit, we will be studying about the stability of the system.